Okay. Very good evening, all. So there is one announcement for the ESE students. Actually, they whatever the extra syllabus you are having, apart from the GATE, so that extra syllabus you will be getting on the Deep Learn platform. Okay, pre-recorded videos are there. Okay, so this is the announcement for ESE students only, and regarding the extra syllabus, right? Okay. So in the yesterday's session, we discussed about single phase fully controlled rectifier. Okay, single phase fully controlled rectifier. Yes. Yeah, for GATE examination, my notes are sufficient, right? Okay. So announcement is for ESE students, those who have taken for the admission for the ESE course. So for ESE students, they are having some extra syllabus compared to the GATE students, right? And for that extra syllabus, there will not be the live sessions, okay? And that extra syllabus will be provided on the Deep Learn platform, right? Pre-recorded videos will be there, okay? So in the yesterday's session, we discussed about okay, yes. So in the yesterday's session, we discussed about the single phase fully controlled rectifier. Now we are going to discuss the single phase half controlled rectifier. Single phase half controlled, or it is also known as a single phase semi converter. Okay, so let me put the heading single phase half controlled rectifier. It is not the half wave controlled. Be careful. It is a half controlled. Okay, it is a half controlled rectifier. It is also known as single phase semi converter or single phase semi converter. So if you check compared to the single phase fully controlled rectifier, in the fully controlled, we are having the four thyristors, okay, four switches, and all the four are the controlled switches. So that's why it is a fully controlled. In the half controlled, we'll be having the two thyristors and the two diodes, okay. So depending on that, there are two types of the half controlled rectifier or a single phase semi converter. One is the symmetrical type, and second one is the asymmetrical. Symmetrical configuration, you can say, and second one is the asymmetrical configuration, right? So in the symmetrical configuration, the circuit diagram, yes. Supply voltage Vs, thyristors are T1 and T2, and diodes are D1 and D2. Okay. Here we're going to discuss the load is a RL load. Why we're going to discuss the RL load, right? You will understand. This is the symmetrical configuration, and next one is the asymmetrical configuration. T1, T2. Diodes are D1 and D2. Okay. Load is RL. Here it is a V0 and here it is a I0, right? So here we are having a single phase semi converter. Semi converter means, or it is also known as a half controlled rectifier. Single phase semi converter is a type of your bridge configuration only. Okay, already we discussed regarding the fully controlled bridge configuration. Now we are going to discuss the half controlled bridge configuration. In the, it is also known as a single phase semi converter. Okay, so you can check compared to the single phase fully controlled bridge configuration. Here we are having, out of the 4 switches, 2 are the thyristors and 2 are the diodes. So here 2 switches are the controlled switches and remaining 2 switches are the uncontrolled switches. Similarly, you can check here also. We're having a controlled switches, these 2, and these 2 are the uncontrolled switches. Okay, so here, yes, we are going to discuss the load only RL. Okay, for R load, what will happen? I will tell you. Okay, so here we are having a VS, that is the VM into sine of omega t, single phase pure single phase pure sinusoidal supply. Same here, VS is also same thing. This is the symmetrical. Why it is a symmetrical? Because if you check here, we are having a 2 legs. This is the first leg, this is the second leg, and each leg consists of 1 thyristor 1 diode. Okay, 1 thyristor 1 diode. Here it is also 1 thyristor 1 diode. That's why it is known as a symmetrical configuration. Whereas if you check here, in the first leg we are having a 2 thyristors, and in the second leg we are having a 2 diodes. Okay, so that's why it is a asymmetrical configuration. Okay, so this is the symmetrical configuration, this is the asymmetrical configuration. Okay, now yes, if you check the circuit operation, okay, if you check the circuit operation, right, what will happen here? If you recall the fully controlled bridge rectifier, right, so we are having the circuit operation like from omega t is equal to alpha till theta. It is like T1 and T2. Okay, means in a fully controlled, I am saying, okay, T1, T2, where in a conduction mode, inductor was storing the energy now. From theta to pi, inductor releases the energy through T1 and T2 only, right? Next, what will happen? From pi to pi plus alpha, again inductor go on releasing the energy through T1, T2. Okay, means if you recall the V0 waveform in a single phase fully controlled rectifier, okay, with RL load and highly inductive load, it is like from alpha to pi plus alpha, only T1, T2 were in a conduction mode. Okay, and if you check the V0 waveform, it was like from alpha to pi, V0 is a positive, and from pi to pi plus alpha, it was like a V0 is a negative. Yes or no? Fully controlled, I am saying. Okay, in a fully controlled. But now in this case, what will happen? In this case, what will happen? Okay, so let us discuss. So here, symmetrical configuration we are going to discuss first. Okay, so Vs is equal to Vm into sine of omega t, right? So when Vs is positive, it is like a plus here and minus here, right? So higher potential here, lower potential here, right? Next, at omega t is equal to alpha, we are going to apply the gate pulse to thyristor T1. So current starts flowing. Yes, from alpha till theta, it is like current is flowing from Vs, T1, load, D2, and again back to the Vs. In this loop, the current will be flowing. Are you getting the point? Okay. So output voltage will be like your supply voltage only. From theta to pi, again inductor releases the energy, T1, D2 will be in a conduction mode. But after pi, actually the inductor releases energy through D1 and T1. Please listen it carefully. I am saying after omega t is equal to pi, inductor releases energy through D1 and T1, because one thyristor is already in a conduction mode. And here we are having a diode. This diode, yes, it is an uncontrolled device now. Okay, so from pi to pi plus alpha, it is like a inductor releases the energy through T1, D2. So if you check here, alpha to pi, T1, D2 conducts. Okay, and from pi to pi plus alpha, T1, D1 conducts. From pi to pi plus alpha, T1, D1 conducts. So my question is, from pi to pi plus alpha, when T1, D1 conducts, that is when inductor releases energy through T1, D1, what will be the output voltage? When inductor releases energy through T1, D1, that is from pi to pi plus alpha, what will be the output voltage? Output voltage is nothing but voltage between these 2 points. Again, you can check this point is connected here, this point is connected here. So from pi to pi plus alpha, when T1, D1 conducts, at that time, the voltage across load is nothing but voltage across these 2 points, right? This point and this point. And here you can check in across these 2 points we're having T1 and D1, and from pi to pi plus alpha all these two devices are in a conduction mode only na. So what is the voltage across these two conducting devices? It is a 0. So from pi to pi plus alpha, yes, it is like a voltage across load is equal to 0 volt. Are you getting the point? Means here the output voltage waveform, right? We are going, yes, we are going to get. It is a similar to that of your RL load in a fully controlled bridge configuration, RL load, but with a freewheeling diode. You can recall fully controlled bridge configuration, RL load, and with freewheeling diode. How we are having the V0 waveform? Alpha to pi, V0 is same as that of the supply voltage. Pi to pi plus alpha, inductor was releasing the energy through the freewheeling diode, na? So what was the V0? V0 is equal to, yes, it was a 0 volt. Same here, instead of the freewheeling diode, now in this case we are having T1 and D1 will be in a conduction mode. Okay, so let me draw the waveform first. Okay, and after that again we will be coming towards the circuit operation, right? So here important point, compared to the fully controlled. Okay, here yes, in the output voltage we will not be getting the negative pulse. Because their inductor, yes, inductor will release the energy through one thyristor and one diode. Okay, one thyristor and one diode. Okay, so the waveform Vs is equal to Vm into sine of omega t, right? Right, this is a Ig1, Ig2, and again Ig1, right? V0 and the I0. The same waveform will be getting for symmetrical as well as asymmetrical configuration. The only thing is conduction of the devices. Okay, that will be different. Yes. And I0 will be a constant current. This is a constant I0. This is like alpha, pi, pi plus alpha, 2 pi, 2 pi plus alpha, and 3 pi. Okay. This is the V0 and I0 waveform I'm saying for symmetrical and asymmetrical. Okay. Both the configurations. Okay. We'll discuss it. Next, let me indicate the conducting devices. Yes, for first symmetrical and second one is for asymmetrical. Symmetrical configuration. Yes. And asymmetrical configuration. Yes, let me write here omega t and conducting devices. Yes, let me write omega t is from alpha to pi, pi to pi plus alpha, pi plus alpha to 2 pi and 2 pi to 2 pi plus alpha. Right? 2 pi to 2 pi plus alpha. Okay. Right? Okay. So now let us discuss one by one. So as I said, in a symmetrical configuration, from omega t is equal to alpha to pi. Okay, at omega t is equal to alpha, we are going to apply the get pulse to thyristor T1 here. Okay, we are going to apply the get pulse to thyristor T1. Okay, so along with the T1, which diode will be in a conduction mode, whether it will be D1 or D2, definitely it will be D2, because you can check when omega t is equal to alpha, Vs is positive now, so it is a plus here, minus here, so here it is a plus, here it is a minus. So it is like thyristor T1 and diode D2 will be in a conduction mode. Okay, so when T1 conducts, along with that D2 conducts. Okay, so current will flow from Vs, T1, load, D2, and again back to the Vs. In this loop the current will flow. Okay, so when the current will flow, what about the V0? V0 is equal to Vs. Okay, V0 is equal to Vs. So from omega t is equal to alpha to pi, definitely between alpha to pi we'll be having the interval like alpha to theta and theta to pi. Actually between alpha to theta, inductor is, yes, inductor will store the energy, and theta to pi, inductor will release the energy. Okay, so between, if you check between omega t is equal to theta to pi, inductor will release the energy through T1 D2 only, because at that time your diode D1 will be in a reverse bias mode only, right? Because you can check the highest potential will be here, means the highest potential will be appearing at the cathode of diode D1 na, right? So when Vs is positive, diode D1 will be in a reverse bias mode. So from theta to pi, definitely our inductor will release the energy through D2 and T1. Okay, D2 and T1. So let me write here, from omega t is equal to alpha to pi, T1 D2 conducts. From alpha to pi, T1 and D2 conducts. T1 and D2 conducts, right? So let me write here, T1 and D2. T1 and D2 conducts. Okay, it is like inductor was storing the energy till theta. After theta, inductor go on releasing the energy. After pi, what will happen? After pi, supply voltage polarity is reversed, na? Right? So it is like a minus here and plus here. So here it is a minus, here it is plus. Now we can check the lowest potential will be appearing at the cathode of diode D1. So definitely our diode D1 will be now forward bias mode, na? Right? So now inductor will go on releasing the energy, right? From pi till pi plus alpha, inductor releases the energy through T1 and D1. Through T1 D1, inductor releases the energy. So when inductor releases energy through T1 D1, what is the V0? V0 is equal to 0 volt na, right? So you can check the waveform. Yes, from pi to pi plus alpha, V0 is 0. Alpha to pi, it is same as that of the supply voltage na. Pi to pi plus alpha, it is a 0. Okay, and during pi to pi plus alpha in symmetrical configuration, which two devices will be in a conduction mode? T1 and D1 will be in a conduction mode. Yes or no? T1 D1 conducts. So let me write here, T1 and D1 conducts. Is this clear? T1 and D1 conducts. Next, at pi plus alpha, we are going to apply the gate pulse to thyristor T2 na. Okay, so we are having thyristor T2 here. So as soon as thyristor gate pulse is applied to thyristor T2, our thyristor T2 starts conduction. Current will flow from Vs, T2, load, D1, and again back to the Vs. Okay, means along with the T2, which diode will be in a conduction mode? Diode D1 will be in a conduction mode, na? Right? So this conduction will be there from omega t is equal to pi plus alpha till 2 pi. Pi plus alpha till 2 pi. Definitely in that pi plus alpha to pi plus theta, it is like inductor stores energy. Okay, pi plus theta to 2 pi, inductor releases the energy. Again, the devices conducting will be T2 and D1 only. Okay, T2 and D1. So you can check when these two devices will be in a conduction mode, what is the V0? V0 is equal to Vs only. Okay, you can apply KVL here, KVL to this loop. We have discussed this multiple times, na? Right? So it is a minus V0 plus Vs is equal to 0. So V0 is equal to Vs. So V0 is positive. Okay, so here you can check from pi plus alpha to 2 pi, V0 is a positive, right? And which two devices will be in a conduction mode? T2 and D1. So let me write here, T2 and D1 conducts. T2 and D1 conducts. Okay. After 2 pi, what will happen? From 2 pi to 2 pi plus alpha. From 2 pi to 2 pi plus alpha. Now our inductor will release the energy through T2 and D2 because T2 was already in a conduction mode. Okay. And after 2 pi, you can check supply voltage polarity will be now reversed. Na? So supply voltage will be like a, yes, here it is a plus, here it is minus. So plus here, minus here, right? So diode D2 will be in a forward bias mode now. Okay. So that's why inductor will release the energy through T2 and D2. T2 and D2 conducts. Okay. So when inductor releases energy through T2, D2, what is the V0? V0 is equal to 0 volt, na? Right? So you can check from 2 pi to 2 pi plus alpha. 2 pi to 2 pi plus alpha. V0 is a 0 volt. Okay. Which two devices will be in a conduction mode? T2 and D2. So let me write here. T2 and D2 conducts. T2 and D2 conducts. Okay. So this is the, yes, conduction of the switches. First of all, T1, D2. After that, T1, D1. Okay. T2, D1 and T2, D2. Right. So you can check here from alpha to pi plus alpha, T1 is in a conduction mode. Pi plus alpha to 2 pi, T2 is in a conduction mode. Similarly, you can check D1. Pi to 2 pi, D1 is in a conduction mode. Na? Pi to 2 pi, D1 is in a conduction mode. And also you can check for D2 also. Yes, 2 pi to 2 pi plus alpha, it is a D2. And at alpha to pi also we are having a D2. Okay. So each diode conducts for pi radian. Each diode conducts for pi radian. Yes or no? You can check D1 conducts for pi to 2 pi. Na? So diode D1 conducts for pi radian. So definitely D2 also is conducting for pi radian. What about the conduction angle of thyristor? Each thyristor is in a conduction mode from alpha to pi plus alpha. Na? So alpha to pi plus alpha means what? It is again pi radian. Okay. T1 also conducts for pi radian. Okay. So important thing here, in a half controlled rectifier or in a single phase semi converter, the V0 waveform, your V0 waveform will not be having the negative pulse. Will not be having the negative pulse. Okay. Because here inductor releases the energy through one thyristor and one diode. One thyristor and one diode. But in this case, if you check compared to that of your REL load with freewheeling diode, and here in this configuration, okay, symmetrical configuration, if you check the average current rating of the thyristor here increases. Na? What is the average current flowing through the thyristor here compared to that of the REL load with freewheeling diode? Yes, here the average current rating of the thyristor increases, and this is the drawback actually. This is the drawback. So that's why generally, yes, a freewheeling diode is connected. Generally, a freewheeling diode is connected across the REL load. Now the question is, suppose in the examination, if they simply say that a single phase semi converter with a REL load, if suppose they doesn't comment anything regarding the freewheeling diode, then we need to consider that yes, here inductor is releasing the energy through T1 D1 as well as T2 D2. Means your waveform will be like this only. Okay. If in the examination, if they say that okay, single phase semi converter REL load with the freewheeling diode, okay, if the statement is like with the freewheeling diode, then here we need to consider the freewheeling diode. And yes, so now when the freewheeling diode will be in a conduction mode, yes, from pi to pi plus alpha, na? Yes or no? And 2 pi to 2 pi plus alpha, that is similar to that of your single phase fully controlled bridge rectifier. Are you getting the point? Is this clear to all? First thing is, definitely this circuit doesn't require a freewheeling diode. But if the freewheeling diode is not used in this circuit, the drawback is, yes, the average current flowing through the thyristor increases. So that's why it will cause the current increase in the current rating of the thyristor. Okay. So that's why in order to avoid this, generally in practical case, okay, in real life, even though the half controlled rectifier is used, but we are using a freewheeling diode also across the REL load. Next, I told you regarding when suppose in the examination, if they simply say that single phase semi converter REL load, okay, and if they doesn't comment regarding the freewheeling diode, then we need not to consider the freewheeling diode across the REL load. We need to consider this operation as it is, okay, this table as it is. But if suppose if they statement like single phase semi converter with the REL load and with the freewheeling diode, then we need to consider the freewheeling diode will be there, and freewheeling diode will be there in the action during which interval? Now you can, yes, can you tell me during this omega t, during which interval the freewheeling diode will be in a conduction mode? Suppose if the freewheeling diode is there in the picture, okay, then during which interval the freewheeling diode will be in a conduction mode? It is similar to that of your fully controlled, na? In the fully controlled bridge configuration, yes, freewheeling diode will be in a conduction mode from omega t is equal to pi to pi plus alpha, as well as from 2 pi to 2 pi plus alpha, na? So here, instead of these two devices, we need to consider the freewheeling diode next. Are you getting the point? So if freewheeling diode is given, definitely we need to consider here freewheeling diode, here also freewheeling diode. If the freewheeling diode is not given, then we need to consider the table as it is. But you can check freewheeling diode is present or freewheeling diode is absent, whether it will change the output voltage waveform. No, output voltage waveform will be getting as it is, na? Are you getting the point? Output voltage waveform will be as it is. It will not change. Are you getting the point, right? So next, so this is actually about the symmetrical configuration. Next, let us discuss the asymmetrical configuration. In the asymmetrical configuration, we are having two thyristors in one leg and two diodes in a second leg. Now suppose at omega t is equal to alpha, okay, Vs is positive, plus minus, where it is plus, here it is minus. At omega t is equal to alpha, the gate pulse applied to thyristor T1. So definitely T1 will conduct, and along with T1, D2 definitely will conduct, because D2 is in a forward bias manner, right? So current will flow from Vs, T1, load, D2, and again back to the Vs. In this loop, the current will flow. Are you getting the point? Okay. Now, yes, if the T1 and D2 are in a conduction mode, what is the V0? V0 will be same as of the supply voltage. So you can check the V0 waveform. It will be same only, na? From alpha to pi, it is like a T1, D2 conducts, and V0 will be same as of the supply voltage. So we'll be getting this type of waveform only. The only thing is which two devices will be in a conduction mode? T1, D2. Here also it was T1, D2. Now here it is also T1 and D2 will be in a conduction mode. So let me write in this alpha to pi, T1 and D2 conducts. T1 and D2 conducts. Okay. Next, after pi, what will happen? Yes, can anyone after pi, what will happen? You can check inductor can release the energy through D1, D2 na here. This is also uncontrolled device. This is also uncontrolled device. So inductor can release the energy either through T1. Yes, inductor can release the energy either through D2 in opposite to that of the supply voltage and through T1, or inductor can release the energy through D1 and D2. But yes, current always follows the path with the lesser opposition. Na? So that's why definitely the inductor will release the energy through D1, D2, because it is like two passive devices. Okay. And these two will be in a conduction mode. Yes, diode D2 will be in a conduction mode due to this inductor here. Okay. So here inductor will release the energy through D1, D2. So after pi till pi plus alpha, which two devices will be in a conduction mode? D1 and D2. Here it was T1, D1, but in this case it is a D1 and D2 will be in a conduction mode. So let me write here D1 and D2 will be in a conduction mode, right? So this is like till pi plus alpha. At pi plus alpha, what we are going to do? At pi plus alpha, definitely supply voltage will be negative, and we are going to apply the gate pulse to T2 na. So it is minus here, plus here, so here it is minus, here it is plus. T2, we are going to apply the gate pulse. Along with T2, definitely D1 will conduct. So current will flow from Vs, D1, load, T2, and again back to the Vs. In this loop, the current will flow. Yes or no? In this loop, the current will flow. So you can check if the current is flowing into this loop, what is the V0? V0 is equal to Vs. Okay, right? V0 is equal to Vs. So with the T2, diode D1 will be in a conduction mode. Okay. So T2 and D1 will be in a conduction mode. And from 2 pi to 2 pi plus alpha, from 2 pi to 2 pi plus alpha, what will happen? After 2 pi, supply voltage polarity will be reversed, na? Means plus here, minus here. So again, inductor will release the energy through D1, D2. Inductor will release the energy through D1, D2. Okay. Means in this case, asymmetrical configuration, right? Yes, from pi to pi plus alpha, as well as from 2 pi to 2 pi plus alpha, inductor is releasing the energy through D1, D2 only, through the diode pair. Okay. So here it is a D1 and D2 conducts. D1 and D2 conducts. So you can check the V0 waveform in both the cases. It will be same. V0 waveform will not change, because you can check when D1, D2 conducts na, when inductor releases energy, that is like a voltage across this branch. That is a voltage across two short circuited diodes na, conducting diodes. So what is the voltage across conducting diodes? It will be 0. So that's why the V0 will be 0 here. Okay. So similarly here you can check. Yes, pi to pi plus alpha, 2 pi to 2 pi plus alpha. V0 is a 0. Right. So we're having the V0 waveform as it is. The thing is, yes, switching of the devices will be different. You can check here. T1, D2 and inductor releases the energy through one thyristor and one diode. Here T1, D2 as it is, inductor releases the energy through two diodes. Inductor releases the energy with through the two diodes. Is this clear? Right? So this is the REL load. Okay, this is the REL load. Now, yes, whether we need to derive the expression for this V0 average, V0 RMS. We already derived, yes, V0 average, V0 RMS, right? Wave expressions for this type of waveform. Okay. The only thing is we can think about conduction time of each thyristor and each diode in both the cases, symmetrical configuration and asymmetrical configuration, right? Okay. So yes, so here right. Okay. Yes. Asymmetrical configuration, yes, it doesn't require, okay, the freewheeling diode, right? Because inductor is releasing energy through the diode pair, right? So that's why the freewheeling diode is not required. So why it is T1 D1 and not T1 D2? T1 D1, not T1 D2. Okay, while releasing energy in symmetrical. Okay. Yes, please listen. As I said, in the symmetrical configuration, inductor releases the energy through T1 D1 from pi to pi plus alpha, releases energy through T1 D1. The question is why it is not releasing the energy through T1 D2? Because you can check from pi to pi plus alpha, na? Inductor is releasing the energy from pi to pi plus alpha. So from pi to pi plus alpha, supply voltage is positive or negative? Supply voltage is negative, means here it is minus, here it is plus, na? So if inductor will release the energy through D2, in opposite to that of the supply voltage T1, okay, means through D2 T1, if inductor releases the energy, so in this path, whether the inductor energy is having a opposition of the supply energy? Yes. Are you getting the point? But whereas if you check, if inductor releases the energy through T1 D1, if inductor releases energy through T1 D1, in this path, is there any opposition? No, na, right? And we know current is having a tendency that it always follows the path with a lesser opposition, right? So that's why inductor will release energy through T1 D1 only. Is this clear? Right? That is one thyristor and one diode pair. Okay, right. And here in the asymmetrical configuration, it is straight. We're having the two diodes, that is the two uncontrolled switches, right? Next, now what about the conduction time of each thyristor and each diode in a symmetrical configuration? Conduction time of each thyristor and each diode in a symmetrical configuration. Yes, thyristor T1 conducts from alpha to pi plus alpha. So what is the conduction angle? Pi plus alpha minus alpha, that is a pi, na? So conduction time is pi by omega. Yes or no? Right? Yes. Okay, so conduction time of each thyristor, okay, let me write it is in symmetrical configuration. Yes, it is pi by omega, right? It is a pi by omega. What is the conduction time of each diode? Conduction time of each diode. Yes, conduction time of each diode. You can check this table. D1 is in a on state from pi to 2 pi. Okay, so what is the conduction angle? 2 pi minus pi. Conduction time pi by omega na, right? So it is a pi by omega again. Pi by omega. This is again symmetrical configuration. Symmetrical configuration. Right? What about the asymmetrical configuration? Conduction time of, yes, each thyristor. Come on. Asymmetrical configuration, conduction time of each thyristor. T1 is in a conduction mode from alpha to pi. T2 is from pi plus alpha to pi. So conduction angle is pi minus alpha and time is pi minus alpha by omega, right? So conduction time of each thyristor. Conduction time of each thyristor. Yes, in asymmetrical configuration. Asymmetrical configuration is equal to pi minus alpha divided by omega, right? Pi minus alpha by omega. Is this clear? What about the conduction time of each diode? Conduction time of each diode. Asymmetrical configuration. Yes, you can check diode D1. Yes, here you can check diode D2. Okay, is in a conduction mode here, okay, as well as here also. And D1 is in a D2 is in a conduction mode, means in this interval, in this interval, in this interval. D2 is in a conduction mode. Sorry, D2 is in conduction from this interval, this interval, this interval. D1 is also in the conduction mode at this interval, at this interval, at this interval. Means each diode is in a conduction mode. Okay, during 3 intervals, na, right? So you can check D1 starts conduction at pi. From pi till pi plus alpha. Pi plus alpha to 2 pi also D1 is in a conduction mode. 2 pi to 2 pi plus alpha also D1 is in a conduction mode. So can we say that the conduction angle of a diode is like a 2 pi plus alpha minus pi? Yes or no? 2 pi plus alpha minus pi. And what is the conduction time? 2 pi plus alpha minus pi divided by omega. Are you getting the point? In the first interval, we don't have the diode D1 in a conduction mode. Okay, so let us, yes, leave that interval. The only thing is, because it is alpha to 2 pi plus alpha, na, that is a one complete cycle, right? So you can check D1 is in a conduction mode from pi till 2 pi plus alpha, right? So let me write conduction time of each diode. It is like 2 pi plus alpha minus pi divided by omega. So it is like a 2 pi minus pi, that is a pi plus alpha divided by omega. Pi plus alpha divided by omega. Is this clear? Right? So you can check this table, right? You will understand. So conduction time of each thyristor, conduction time of each diode here. Is this clear? Right? Next. So this is about and remaining things, average value, RMS value, we can derive it. Okay. Why it is for RL load I have discussed. You can check. Suppose if RL load is replaced with a R load, what is the operation? Suppose if RL load is replaced with a purely resistive load. Yes, from omega t is equal to alpha to pi. Which two devices will be in a conduction mode for purely resistive load? Come on. From omega t is equal to alpha to pi. Suppose if the load is purely resistive, which two devices will be in a conduction mode from alpha to pi? In a symmetrical, it is a T1, D2. Yes or no? In asymmetrical also T1, D2. Right? So T1 and D2 will be in a conduction mode. Right? So yes, T1 and D2 will be in a conduction mode. Now only resistor suppose if present, whether the inductor will store the energy. Inductor is not there now. So there is a no issue, like there is no point like storing energy and releasing energy. Pi to pi plus alpha, what will happen? Circuit will be at the rest position now, right? So from pi to pi plus alpha, it is like a circuit will be at the rest position, right? So your V0 will be 0 only. None of the device will, none of the switch will be in a conduction mode. Pi plus alpha to 2 pi, pi plus alpha to 2 pi, again T2 D1 will be in a conduction mode na. Pi plus alpha to 2 pi, T2 D1 conducts. Okay. So like this means operation will be similar to that of your fully controlled converter or the fully controlled bridge rectifier only. Okay. But the thing is, instead of the 4 thyristors, we are having a 2 thyristors and 2 diodes. Okay. So that's why it is a single phase semi converter. Now my question is, in a single phase semi converter, with a REL load, highly inductive load, let us consider, such that I0 is equal to capital I0. Okay, I0 is equal to capital I0. How will be the waveform of the IS, source current waveform? Single phase semi converter, how will be the waveform of the IS? Yes, from omega t is equal to alpha to pi. What will the IS? Whether it will be same as that of the capital I0, whether it will be opposite to that of the capital I0, that is minus I0, or it will be something different. Yes, my question is, from omega t is equal to alpha to pi, what is the IS value? I0 na, right? It is equal to I0. We discussed it in the yesterday also. Okay, so IS waveform, if we want to draw, right, for IS waveform, omega t 0 alpha pi plus alpha and 2 pi. Yes, from omega t is equal to alpha to pi, T1 D2 conducts na, T1 D2 conducts here also and here also. IS is equal to capital I0. Okay, so IS is equal to capital I0. So the waveform will be like this, alpha to pi. From pi to pi plus alpha, what is IS? Come on. From pi to pi plus alpha, what will be the value of IS? Pi to pi plus alpha, inductor releases the energy na, through T1 D1 in the symmetrical configuration, and in asymmetrical through D1 D2. So what is the IS? It will be 0, it will be non-zero. Come on, speak out. Yes, it is a 0 na, it is a 0, right? It is a 0. Yes, so let me write here, pi to pi plus alpha, it is a 0, because source is not connected to this your circuitry na, because T1 is in off state. Okay, next, pi plus alpha to 2 pi, plus alpha to 2 pi, what will happen? IS value, pi plus alpha to 2 pi, which two switches will be in a conduction mode? T2 D1 na. So current is flowing like this, Vs T2 load D1 and again back to the Vs. In this loop current is flowing. So in this loop, if the current is flowing, what is IS? Plus I0 or minus I0? Yes, it is equal to negative, right? Minus I0, right? Minus I0. Pi plus alpha to 2 pi. And next, 2 pi to 2 pi plus alpha means it is like a 0 to alpha. Okay. So from 0 to alpha, or you can say 2 pi to 2 pi plus alpha, what is IS? It will be 0 na, because inductor releases the energy. So this magnitude is plus I0. This magnitude is minus I0. So this is the waveform of the source current. Yes, what is the nature of this? Whether it is a square wave or quasi square wave? It is a quasi square wave na? We discussed it. Okay. For REL load with freewheeling diode also, we are having this type of waveform. Yes or no? Right? And REL load without freewheeling diode. Yes, how is the waveform? In a fully controlled bridge configuration, REL load without freewheeling diode, how is the IS waveform? It is a square wave na? We are having a square wave. But in the REL load with freewheeling diode, in a fully controlled, I am saying, we are having this type of waveform only. So please keep it in mind. Your single phase semi converter with REL load, it behaves as single phase full converter only with a freewheeling diode. Single phase full converter with a freewheeling diode. Is this clear? Right? So both are same. Single phase full single phase fully controlled bridge converter or the rectifier with REL load and with freewheeling diode, and your single phase semi converter with REL load, you will be getting the same waveforms. Are you getting the point? Right? Because in the with the freewheeling diode, the inductor releases the energy through the freewheeling diode. In the semi converter, inductor releases the energy if it is a symmetrical through 1/1 diode, if it is a asymmetrical through the pair of the diodes. Right? Is this clear? Right? Okay. Sir, explain how D2 conduct at pi to pi plus alpha in asymmetrical operation. Okay. Yes, in asymmetrical, pi to pi plus alpha, na? Pi to pi plus alpha. So you can check after pi supply voltage is negative, means minus here, plus here. So this is like a plus will appear here, na? Right? And minus will appear here. But you can check pi to pi plus alpha. It is like near to the pi. What is the value of Vs? Vs value is very less. Okay, so that's why your potential comparatively less. So due to the whatever the energy stored by the inductor earlier, okay, due to that inductor voltage will be greater than that of whatever the potential here. So that's why your D2 will be in a conduction mode only, forward bias mode only, right? So D1, D2 conducts here, right? So this is about your single phase semi converter. They have asked the question. So please keep it in mind. Till now we have discussed the single phase half wave controlled uncontrolled rectifier, single phase half wave controlled rectifier. Next, single phase full wave controlled rectifier, center tapped transformer configuration, bridge configuration. In the bridge, we discussed the fully controlled, and this one is a semi converter, or it is also known as a half controlled. It is also known as a half controlled. Now moving towards the next point is the how to calculate the input power factor if the load is a highly inductive, because yet we have not discussed regarding the input power factor when the load is REL load or RELE load, right? Why we have not discussed, you will understand it now. Okay, for purely resistive load we can calculate it by equating the input power is equal to output power. Okay, but if the load is REL load or RELE load, then the thing is you can check supply voltage you are having, it is a purely sinusoidal, but you can check the supply current for REL load or RELE load. If the load is highly inductive, na, we're having a supply current is like a square wave, na, right? Or it is a quasi square wave, means we're having the supply current waveform either this one or it is a 180-degree square. 180-degree square wave mode means what? From alpha to pi plus alpha, it is I0 only. Means it is just like your REL load without freewheeling diode case. Okay, means this is IS waveform is your non-sinusoidal, Vs waveform is a sinusoidal. Okay, so that's why if that is the case, if supply voltage is sinusoidal, supply current is non-sinusoidal, then how to find the input power factor? For that we are having a different method. Okay, so that we are going to discuss now, right? Okay, so okay, yes, so yes, put the heading input power factor for RL and RLE load. Okay, input power factor for REL and RLE load. Okay, so in this, let us first discuss how to find the input power factor, and after that we'll be moving towards the very important tool from the mathematics and very famous tool from the mathematics, that is the Fourier series. Okay, that we are going to discuss. Don't lose the concentration. This is very important bit. Number of times they have asked the question, right? So yes, input power factor. So how to find the input power factor if your supply voltage is sinusoidal and supply current is a non-sinusoidal. Okay, so if Vs is a sinusoidal and Is, that is a source current, is a non-sinusoidal, then input power factor is calculated, yes, by using following expression. Following expression. So what is that expression? IPF means input power factor is equal to distortion factor into displacement power factor, right? Distortion factor into displacement power. IPF means input power factor is equal to DF, distortion factor, into displacement power factor. What is the distortion factor? What is the distortion factor? Yes, where DF is a distortion factor. Distortion factor. And DPF is a displacement power factor. Displacement power factor. It is also known as a fundamental power factor also. Okay, it is also known as a fundamental power factor. Okay, displacement power factor, or let me write it as a fundamental power factor. So here, let us understand what is a DF, distortion factor. So distortion factor. Yes. Distortion factor means it is a ratio of RMS value of fundamental source current to the RMS value of the source current. I am using the word fundamental source current, okay, to the source current, RMS value of the source current. Okay, so distortion factor, it is ratio of RMS value of fundamental source current. What is a fundamental source current? That you will understand, okay, during the discussion on Fourier series. Okay, RMS value of fundamental source current, right? It is the ratio of RMS value of fundamental source current. That is nothing but, let me write it as a IS1 RMS. IS1 RMS to RMS value of source current. Source current, that is a IS RMS. IS RMS. So that is nothing but your distortion factor is equal to IS1 RMS divided by IS RMS, right? So IS RMS we know, right? IS RMS means if it is a fully controlled bridge configuration, RL load, highly inductive load, okay, if the freewheeling diode is not there, then IS RMS, it is a square type of waveform. Na? So from that we can find IS RMS. Okay, so how to find the IS1 RMS we will discuss. Okay, so distortion factor is this thing. Second thing, we are having a displacement power factor, DPF, that is a displacement power factor. So what is a DPF? Let us understand. Displacement power factor. It is, yes, it is cosine of angle between, it is cosine of angle between fundamental source voltage, fundamental source voltage, fundamental source voltage, that is nothing but VS1, and fundamental source current, and fundamental source current, that is IS1. Means what? Displacement power factor means cos of angle between VS1 and IS1. Okay, so displacement power factor is equal to cos of, yes, angle between VS1 and IS1. VS1 and IS1, right? Next. So now let us discuss how to find that IS1 expression, how to find that VS1 expression. Okay. So for that, we are going to introduce now the Fourier series. Okay. Or you can say the Fourier series analysis. Okay. Fourier series analysis. What is the Fourier series? Fourier series is a tool that that gives the expression for non-sinusoidal periodic signal, okay, in terms of the sinusoidal term, in terms of the sinusoidal functions, okay. That is nothing but your Fourier series, right? Means the important thing is for Fourier series, the first thing is we require a periodic signal. We require a periodic signal. Now, Fourier series is generally related to your fundamental component and a harmonics. If you check in electrical engineering, the very wide domain we are having, that is the harmonics, okay. And in a Fourier series, we are going to just introduce, or we are going to just touch the different harmonics, okay. Means from the Fourier series, you can check, you can observe, you can get which harmonics will be present, okay, in the source current waveform, in the source current waveform. Please yes, don't lose the concentration here, because same Fourier series we are going to use in an inverter also. In an inverter also, we are having the how to reduce the harmonics, okay, how to find the percentage share of the fundamental, okay, in the output voltage of the inverter, like this, okay. So yes, so let me put the heading Fourier series analysis. Fourier series analysis. Yes. According to the Fourier series, any periodic signal, okay, any periodic signal can be represented as, yes, it is represented as, let me write it as f of t is equal to, yes, a0 by 2 plus summation over n is equal to 1, 2, 3 up to the infinity an into cos of n omega t plus bn into sin of n omega t, where a0 by 2 is nothing but average value. It is a average value of f of t, average value of f of t. an is equal to 2 by t integration from 0 to t, okay, 2 by t integration from 0 to t. It is a f of t into cos of n omega t d omega t, and bn is equal to 2 by t integration from 0 to t f of t into sin of n omega t into d omega t, right? You need to memorize these expressions. Yes, Fourier series generalized expression of any periodic signal. Suppose f of t is a function or it is a signal in time domain, then how it is expressed? The first thing is that signal or that function is a non-sinusoidal, but it is a periodic, okay. So it is a0 by 2. A0 by 2 means is nothing but the average value, okay, average value of that signal or a function, plus summation over n is equal to 1, 2, 3 up to the infinity an cos of n omega t plus bn into sin of n omega t. What is the an? An is this term. It is equal to 2 by t integration from 0 to t f of t into cos of n omega t d omega t, okay. And bn is equal to 2 by t integration from 0 to t f of t into sin of n omega t into d omega t, right? Or either in time domain, if we want, we can write it as like this dt also, okay, because limit is here 0 to t. So let me write it as dt. While simplifying, we'll convert it into d omega t, okay, we'll convert it into d omega t, right? So definitely here also it is a nt, that should be nt. Next, so now these are the three terms we need to memorize, okay, and by considering these three terms, now we are going to proceed, okay. So let us first do the Fourier series analysis, okay, of the source current waveform of single phase fully controlled bridge rectifier, single phase fully controlled bridge rectifier with RL load and RLE load. Okay, RL load, and because we discussed yesterday session, if even though the if load is RLE and if L is highly inductive na, then it is like a effect of E will not be observed in the V0 na, right? So we'll be having the constant current I0 only, right? So let me put the heading. Yes, single phase fully controlled, single phase fully controlled rectifier. Okay, either you can say RL load, RLE load, right? For both it is applicable, RL or RLE load. Yes. Now if you check single phase fully controlled rectifier, RL load or RLE load, how is the waveform of IS we are having? We are having IS waveform like this. Yes, it is with respect to omega t, yeah? Right? 0 to alpha, alpha to pi, pi to pi plus alpha, pi plus alpha to 2 pi we are having, right? So you can recall the IS waveform from alpha to pi plus alpha, it is a positive. Yes or no? Pi plus alpha to 2 pi plus alpha, it is a negative. 2 pi plus alpha is nothing but suppose this point. So it is a negative now. So in this case also it will be like 0 to alpha, that will be negative. Yes or no? 2 pi to 2 pi plus alpha is nothing but your 0 to alpha only, right? So it is like your I0 and this is a minus I0. Minus I0. Now, whether this IS waveform is a even signal or odd signal, you might have studied the signal system. Yes or no? Have you studied the signal system? Yes, no. Yes, I will tell you, Shiva, what is the meaning of fundamental source current. Okay, have some patience. Yes. Okay. So in the signal system, yes. How to find whether the function is a even or odd? Okay, let me write that first. Even function or even signal, you can say. The function is said to be even. Okay, if f of minus t is equal to f of t. F of minus t is equal to f of t. Just like your cosinusoidal, cosine waveform, right? It is a even signal, it is a even function. And odd function means your f of minus t is equal to minus f of t. Just like your sinusoidal function. You can check sinusoidal is a odd signal, whereas cosinusoidal is a even signal, right? Minus t means time is negative and plus t means time is positive. You can check cosinusoidal we are having like this. This is a cos waveform, na? And at this side, if you check in the continuous case, it will be like this, na? So if this is f of t for cos, this is like a t. So you can check at t at this instant, f of t is having this value, na? Let me write as t dash. So at minus t dash, it will be having this value. This is this indicates your minus t dash. So f of minus t dash is nothing but this value, and again which is equal to f of t dash, na? So same values we are having. So it is a even signal. Similarly, you can check for the sinusoidal. Sinusoidal is like this, na? From here it is starting 0, and for before that it will be negative. Okay, so that's why it is an odd signal, right? Next, now so we are having a even signal, odd signal. Now if you check this IS waveform, this is neither even nor odd. This is neither even nor odd. Okay, so and in the Fourier series, we are having some conclusions. If the signal is okay, if the signal is an odd signal, then value of an is 0. If the signal is an odd signal, then the value of an is a 0. So let me write Fourier series conclusion. Fourier series conclusion. Yes. For odd signal, an is equal to 0. An is equal to 0. Okay. Now, yes, here if you check, this signal is neither even nor odd. Okay, because you can check if this is 0 to alpha. Yes, from 0 till 2 pi na, from 0 till 2 pi, it is like one cycle complete of this signal. Okay, so 2 pi to 2 pi plus alpha, whatever the signal we are having, that is the negative value na, right? That negative, okay, will be here at this side. Okay, right? So here from this waveform we cannot generalize that whether it is a even or odd. So for that, what I am going to do, I am simply yes, shifting this signal. I am simply shifting this signal to the left hand side. Okay, by alpha angle, by angle alpha. Please try to understand what I am doing. Definitely our IS is like this only. We are going to write the Fourier series expression of this IS only, for this IS only. Now, in order to take the advantage of this conclusion of the Fourier series, okay, what I am going to do, I am going to shift this IS, okay, by alpha angle, by alpha radian to the left hand side. So if I shift this signal or this waveform by alpha radian to the left hand side, how it will look like, you can check. If I shift this alpha to this 0 na, okay, so it will be looking like, means our signal will start from 0, and from 0 till pi it will be I0, pi to 2 pi it will be minus I0. Yes or no? Means it is alpha to pi plus alpha, we are having a pulse width. If I shift this signal by alpha radian to the left hand side, then we'll be getting the I0 will be from 0 to pi. Instead of alpha to pi plus alpha, it will be from 0 to pi. So let me, yes, indicate that IS dash. I'm writing it as a IS dash. Omega t 0 to pi, pi to 2 pi. So this type of signal will be getting. Okay, so means I have shifted this signal, this waveform, by alpha radian to the left hand side, so that after shifting I will be getting this type of waveform. This value is a plus I0 and this value will be minus I0. This is a minus I0, this is a plus I0. Now you can check this waveform. Yes, before 0, which cycle will be there? You can check. Here it is a positive cycle, here it is a negative cycle. Again we'll be having positive cycle, again we'll be having a negative cycle na, right? So similarly before this, because in we know na, it is a omega t 0, means it is like omega t is 360 degree again. Okay, so whatever the waveform we're having from pi to 2 pi, the same cycle will repeat here na. Yes or no? Means again before this positive will be having the negative cycle. So now if before this positive, if we will be having the negative cycle, can I say that this signal will be your odd signal? You can check na. Yes, IS dash of t minus t is equal to what? Minus of IS dash of t. So that's why it is an odd signal. Right? So now IS dash is a odd signal. So if IS dash is an odd signal, definitely its AN is equal to 0. If you want, you can calculate the AN by using this expression. You will be getting 0 only. For this signal. I am saying. Okay. But we are having a ready conclusion from the Fourier series. That's why I am directly using that ready conclusion. Okay. And in order to use that, in order to take the advantage, okay, so I have shifted that signal, okay, by alpha radian to the left hand side. Now, yes, so AN value is 0, no problem. What about the A0 by 2 value? Because in order to represent this IS dash Fourier, in order to write the Fourier series expression of this IS dash, yes, we need to find A0 by 2, we need to find AN, we need to find BN. Na? AN is already 0 because it is an odd signal, right? AN is 0. Now we need to find a0 by 2. We need to find a0 by 2 and bn also. So now my question is, what is the a0 by 2 for this signal? A0 by 2 means the average value. What is the average value of this signal? Yes, can anyone? What is the average value of this is dash? Yes, average value of is dash is a 0 only, na? Right? So can I write a0 by 2 is equal to 0, right? So therefore a0 by 2, a0 by 2 is equal to average value, okay, average of is dash. I have represented it as a is dash. First of all, we are going to derive the expression of Fourier series for is dash, and after that we are going to write for is. Okay, so average value of is dash is equal to 0. So your a0 by 2 is also 0, an is also 0. Now our next task is to find the bn value. Our task is to find the bn value. So now you can check in the bn we are having it is 2 by t. What this capital T indicates? The capital T is nothing but the periodic time, okay, time period of the signal. So instead of time, now can we write it in terms of angle, because we're having the signal is dash, it is in with respect to omega t na? So now what I am going to do, I am going to modify this expression of bn, okay, as instead of this time I am going to consider the periodic angle. I am going to write the periodic angle instead of the time limit, okay. I am going to put the angle limit, and instead of this time, right, t, we are going to replace it with the omega t, and instead of this dt we are going to replace it with the d omega t. Okay, so please listen how to find the bn, how to find the bn, right? So let me write here, bn is equal to, yes, it is a 2 by t na, it was a 2 by t. Now instead of t, as I said, we need to, instead of time we are going to take the periodic angle. So what is the periodic angle of this signal? It is a 2 pi na. After 2 pi again the same waveform will repeat, yes or no, right? So periodic angle is 2 pi. So it is equal to 2 by 2 pi. Integration from 0 to t it was there, okay, but instead of time we can take it as 0 to 2 pi. Angle I am writing, okay. Yes, it is a value is dash na, because if you check this expression f of t was there, instead of f of t now I am writing is dash into, yes, you can check bn, yes, sine of n t na. So instead of t it is a sine of n omega t into sine of n omega t into d omega t. Now here we need to simplify this integration. Is dash, you can check 0 to 2 pi. Is dash is yes, having two intervals, 0 to pi and pi to 2 pi. During 0 to pi, is dash is plus I0, pi to 2 pi, is dash is minus I0, right? So let me write it as, therefore bn is equal to 2 by 2 pi means it is like 1 by pi. This 0 to 2 pi can be divided as 0 to pi. During 0 to pi, what is is dash plus I0? So it is I0 into sine of n omega t into d omega t plus integration from pi to 2 pi. It is a minus I0. No? During pi to 2 pi, what is is dash? Minus I0 into sine of n omega t into d omega t. Now can we further simplify it? Can we take I0 outside? Yes, so it is a I0 upon pi into, you can check, integration of sine of n omega t. It is a minus cos of n omega t. So let me write it as minus cos of n omega t. Okay, and integration is with respect to d omega t. Na? So divided by n we need to write limit 0 to pi. Minus this as it is, and integration of sine is minus cos, that minus and this minus plus. So it will be cos of n omega t divided by n, limit pi to 2 pi. Right? Further, can we take this divided by n common? Yes, so it is a I0 by n pi. Let me write it as I0 by n pi. So therefore bn is equal to I0 upon n pi into, it is like a minus cos of n pi plus cos 0 na, right? So it is like cos of n pi minus actually plus cos of 0. This is the one thing. Put the limit here, cos of 2n pi minus cos of n pi. Okay, so plus cos of 2n pi minus cos of n pi. So further we can write it as I0 upon n pi into cos 0 is 1. What is cos of 2n pi? You can check for any value of n. What is the value of cos of 2n pi? Suppose n is equal to 1. Cos of 2 pi, 1 only. That is cos 360. Na? N is equal to 2. Cos of 4 pi, 1. N is equal to 3. Cos of 6 pi, 1. N is equal to 4. Cos of 8 pi, 1. Okay. Means for all values of n. For all values of n. Yes. Can I write this term will be equal to 1 only? Yes or no? This term is 1 and this term is also cos 0 means this term is also 1. Right? So now can we write it as? This is a 1 plus 1, that is a 2. Minus cos of n pi minus cos of n pi. So it is a minus 2 into cos of n pi. Now what is the cos of n pi? You can check. N is equal to 1, it is a cos pi. Cos pi is plus 1 or minus 1? Minus 1. N is equal to 2. You can put here n is equal to cos of 2 pi. Cos 2 pi is plus 1. N is equal to 3. Cos 3 pi. Cos 3 pi is minus 1. N is equal to 4. Cos 4 pi. Yes, it is a cos 4 pi is plus 1. Means, can we say that for odd values of n, it is a minus 1. And for even values of n, it is a plus 1. So can we write it as I0 upon n pi into 2 minus 2 into minus 1 to the power n. I have replaced this cos n pi with minus 1 to the power n. You can check n is equal to 1, it is a minus 1. N is equal to, it is a plus 1. N is equal to 3 minus 1, right? So further we can write it as 2 into I0 divided by n pi into, it is like 1 minus minus 1 to the power n. This is your Bn expression. This is the Bn expression. Now, yes, check the expression, check the value of Bn for different values of n. Okay, check the value of Bn for different values of n, I am saying. Okay, so suppose, yes, okay. So for n is equal to 1, what is Bn? For n is equal to 1 means simply here put n is equal to 1. Here it is n is equal to 1. You can check 1 minus n, 1 minus minus 1 to the power 1. Minus 1 to the power 1 means minus 1. So this minus 1 and this minus plus. So 1 plus 1, 2, 2 into 2, 4. So it is 4 I0 by pi. Na? Yes or no? Right? So for n is equal to 1, Bn is 4 into I0 divided by pi. Check for n is equal to 2. N is equal to 2. Yes, what is the Bn? Minus 1 to the power 2. Minus 1 square. It is a plus 1. Na? So that plus 1 bracket and here it is minus 1. So it is a minus 1 minus 1, 0. Na? Right? So for n is equal to 2, it is 0. N is equal to 3, you can check Bn. N is equal to 3. Put here n is equal to 3. Minus 1 to the power 3. So it is a minus 1. So minus 1 and this minus. So it is plus 1 plus 1. 2, 2 into 2, 4. And here it is 3. Na? So it is a 4 into I0 divided by 3 pi. Check for n is equal to 4. Bn is equal to, yes, put here n is equal to 4. 1 minus minus 1 to the power 4. Minus 1 to the power 4 is plus 1. Na? And that plus 1 and here it is minus. So this bracket will become 0. So that's why it is 0. You can check for n is equal to 5. You will be getting it is a 4 I0 divided by 5 pi. N is equal to 6. It is a 0 and so on. So now from this, yes, you can check. N is equal to 1, Bn is 4 I0 by pi. N is equal to 2, it is 0. N is equal to 3, it is 4 I0 by 3 pi. N is equal to 4, it is 0. N is equal to 5, it is 4 I0 by 5 pi. N is equal to 6, it is 0. So can we say that n is equal to 2, n is equal to 4, n is equal to 6, it is 0. Similarly, you can check for n is equal to 8, n is equal to 10, 12, 14, 16, 18, etc. You will be getting Bn is 0 only. So can we say that the value of Bn is equal to 0 for all even values of n? Yes or no? Right? So let me write Bn is equal to 0 for all even values of n. Okay. And what about the Bn value for odd values of n? It is a 4 I0 by n is equal to 1 means 4 I0 by pi. N is equal to 3, it is 4 I0 by 3 pi. N is equal to 5, 4 I0 by 5 pi. So can we write it is a 4 into I0 divided by n pi for, yes, odd values of n. Are you getting the point? Okay, means for even values of n, bn is 0. For odd values of n, bn is 4i0 by n pi. Now we have calculated a0 by 2, that is the average value, it was 0. We calculated an value. Due to the odd signal, an is also 0. The only thing is bn is there. Okay, only thing is bn is a non-zero. But in that also, bn is a 0 for even values of n, and for odd values of n, bn is 4i0 by n pi. Yes or no? So now can we write the expression of is dash? Right? Is dash. How to write the is dash? Therefore, according to Fourier series, is dash. What is is dash we are having? You can check this expression. Yes, this expression we are having a standard. So f of t means general function we considered. Now instead of f of t, consider is dash. It is a a0 by 2, but a0 by 2 is already 0. an into cos of n omega t. An is 0 na? So only thing is we need to write this term, bn into this term. But in that also, whether bn is non-zero for all values of n? No, bn is a non-zero only for odd values of n. Na? So in this summation also we can modify as n is equal to 1, 3, 5, 7 up to the infinity bn into sine of n omega t. Right? So let me write it as, yes, is dash is equal to summation over n is equal to 1, 3, 5, 7 up to the infinity. Are you getting the point? Why I have not written here n is equal to 2, n is equal to 4, n is equal to 6? Because corresponding to the all even values of n, our bn is 0. This bn is 0. So that's why only for odd values of n, bn will be non-zero. And what is the value of bn? 4i0 by n pi. So it is a 4 into i0 divided by n pi into sine of n omega t. Yes or no? This is the expression of is dash. This is the expression of is dash. This is not the expression of is. This is is dash expression. Now from this expression, we can write the is expression. How to write the is expression? Let us discuss. Okay. Is this clear to all? Right? Simple steps we need to follow. We are having the general expression. This is the general expression. We are having a0 by 2 means what? An how to find, bn how to find. Okay. So for next, this is the is we are having. This is neither even nor odd. So for that, what we have done? Yes, what we have done? I have shifted this is, okay, to the left hand side by alpha radian. So after shifting, yes, we got this is dash, and after that we have derived the is dash Fourier series expression. Now from this is dash, now we need to write the is. Okay, so now Fourier series expression. Fourier series expression of is. Okay, of is, right? So you can check here, is dash and is we're having. This is the is dash, okay, and this is the is we're having. Now by observing these two waveforms, is dash and is, yes, can I say that is is lagging to is dash? I'm saying is is lagging to is dash by alpha radian. If I shift this waveform by alpha radian to the right hand side, I will be getting this is na. So can I say that is lagging to is dash by alpha radian? Yes or no? Right? So let me write here as is dash is lagging to is. Sorry, is is lagging. Is is lagging to is dash, right? Yes or no? This is is dash, and here it is a is na. Is is lagging to is dash, okay, by alpha radian. Yes, yes, I will tell you how the n value is 0. Okay, okay. So as is is lagging to is dash, this is is dash, okay, by alpha radian, okay. And you can check, we are having expression, Fourier series expression of is dash. So now what we can do, simply in order to write the Fourier series expression of this IS terms as it is, n is equal to 1, 3, 5, 7 up to the infinity. Means after 7 there will be 9, after 9 there will be 11, after that 13, after that 15, after that 17, 19, 21, 23, etc. up to the infinity. Okay. Yes, it is a 4 into I0 divided by n pi. Now here sine of, instead of this omega t na, we need to write omega t minus alpha, because is is lagging to is dash na. So here instead of angle is omega t minus alpha. Instead of this omega t, here angle will be omega t minus alpha. That is the only change, right? Means first we calculated, we have derived the expression of is dash Fourier series expression, and next we have written here Fourier series expression of this is. Please try to understand, this n should be out of this bracket. It is a n into omega t minus n into alpha actually, strictly speaking. Okay. So it is n into bracket omega t minus, means I need to replace this omega t with omega t minus alpha, because is is lagging na. Is is lagging to is dash by alpha radian, Okay. So now this is the Fourier series expression. Fourier series expression of is, that is the source current, okay, which we drawn for RL load or RLE load without freewheeling diode. In the case of your fully controlled bridge configuration, means this expression is for which waveform? This expression is for this waveform na, is, right? Now you can check this waveform carefully. This is very important expression, and it gives a lot of information, right? What it indicates, actually our is is like this. Actually our is is like this. This is a square wave. Okay, it is a shifted square wave we are having. But according to this expression, can we say that our is waveform, that is nothing but the square wave waveform, it is a summation of yes, various sinusoidal waveforms. It is algebraic sum na. For various sinusoidal, I am saying for n is equal to 1, it is a 4I0 by pi into sine of omega t minus alpha. N is equal to 3, 4I0 divided by 3 pi into sine of 3 into omega t minus alpha. N is equal to 5, 4I0 divided by 5 pi into sine of 5 omega t minus alpha. So further, can I write this as is? Therefore, we can write is is equal to, yes, let me write it as 4I0 divided by n pi. For n is equal to 1, let me write first. Okay, so it is a 4 into I0 divided by pi into sine of n omega, sine of n is equal to 1 na? For n is equal to 1, it is a omega t minus alpha. I have written this for n is equal to 1 only. Plus, it is algebraic sum na, so plus n is equal to 3 means 4I0 by 3 pi into sine of 3 omega t minus 3 alpha na, right? So it is 4I0 divided by 3 pi into sine of 3 omega t minus 3 alpha, plus n is equal to 5 means 4I0 by 5 pi into sine of 5 omega t minus 5 alpha. 4 into I0 divided by 5 pi into sine of 5 omega t minus 5 alpha. The meaning is, and so on. Okay, after 5th we'll be having a 7, 9, 11 and so on. Okay, so now please try to understand what is the meaning of this term. Here you can check whatever the waveform we're having is, it is a square wave na? And it is a summation of this sinusoidal waveform, this sinusoidal waveform, this sinusoidal waveform. After that the 7 will come, after that the 9 will come, after that 11 will come, etc. But you can check it carefully. Here this is corresponding to n is equal to 1 na? This is corresponding to n is equal to 1. This is corresponding to n is equal to 3. This one is for n is equal to 5 na? So what it indicates, n means what? Please try to understand. Here you can check, this indicates this term 4I0 by pi into sine of omega t minus alpha. This indicates the source current value. Okay, in the source current for n is equal to 1. Okay, we are having this waveform. The meaning is this is the fundamental component. We are having n is equal to 1, 3, 5, 7 na? The meaning is n is equal to 1 means our fundamental component. N is equal to 3 means third harmonic component. n is equal to 5 means fifth harmonic component, n is equal to 7 means seventh harmonic component. So it is like a source current, okay, at a fundamental component, For fundamental, I am using the word only fundamental component. But for third, I am using the word third harmonic. For the fifth, I am using fifth harmonic. But for fundamental, I am not using the word fundamental harmonic. Please be careful. Fundamental is not your harmonic. Fundamental is a component. After fundamental, whatever it may be, that is a second, third, fourth, fifth, sixth, seventh, etc. All will be the harmonics. All will be the harmonics. Are you getting the point? So fundamental is a component only. Suppose if we are having a pure sinusoidal waveform, the meaning is harmonics in that waveform will be absent. Means only fundamental component will be present. Are you getting the point? Please try to understand this statement. If we are having a pure sinusoidal waveform, just we discussed, okay, in every circuit we consider that Vs is a pure sinusoidal. Na? The meaning is we are saying that Vs is a pure sinusoidal means that Vs waveform is not consisting of any harmonics. Means only fundamental component is present. Means whatever the Vs waveform we are having, that's Vs waveform is nothing but a fundamental component of the Vs only, right? Because it is a pure sinusoidal. But whereas if you check the Is waveform, right, whatever the Is waveform we got now, that Is waveform is it is a non-sinusoidal, it is a periodic signal. The meaning is at the back side, okay, that waveform is equal to what? Addition of all these sinusoidal components. Okay, sinusoidal components. Now you can check if this is the fundamental component, this is the third harmonic, this is the fifth harmonic component. Now we can observe here. This 4I0 by pi means what? 4I0 by pi means it is a peak value. It is a sinusoidal function first of all. Yes. First of all, this is a sinusoidal function. Yes or no? And for if this is a sinusoidal function, then what this 4I0 by pi indicates? It is a peak value of this sinusoidal. Similarly, for third harmonic also we are having a sinusoidal function. What is the peak value of that sinusoidal third harmonic? It is a 4I0 by 3 pi. Here it is a 4I0 by pi. Here it is a 4I0 by 3 pi. For fifth harmonic, it is a 4I0 by 5 pi. For seventh, it will be 4I0 by 7 pi. For ninth, it will be 4I0 by 9 pi. So what is the meaning of that? As the order of harmonic increases, its peak value as well as its RMS value go on decreasing. Are you getting the point? You can check the fundamental is having a highest peak value compared to that of third harmonic. You can check third harmonic peak value is 1/3 of the fundamental. Na? Fundamental peak is 4I0 by pi. Third harmonic peak is 4I0 by 3 pi. So that's why it is a 1/3 of the fundamental. Fifth harmonic peak value is a 1/5 of the fundamental. So as the order of harmonic increases, definitely its peak value go on decreasing. And as this is the sinusoidal function, we know for any sinusoidal function, RMS value is nothing but peak value divided by √2, na? Right? So therefore, if peak value are decreasing, definitely the RMS value of that respective harmonics will be decreasing only. Right? So this is the one important statement. As the order of harmonic increases, its peak value as well as RMS value will be decreasing only. Second thing, now you can check the frequency. For the fundamental, what is the frequency? Omega. For the third harmonic, frequency is 3 omega. For the fifth harmonic, frequency is 5 omega. So what it indicates? As the order of harmonic increases, the frequency increases. Are you getting the point? Okay. So please try to understand these two statements are very important. If the order of harmonic increases, then its peak value as well as RMS value decreases. Order of harmonic increases, its frequency increases. So that's why in many cases you might have heard the statement, or in any book you might have read the statement like, generally we are worrying about the lower order harmonics only. Why? Because if the order of the harmonic is lesser, its share, its peak value, that's why it is the RMS value, that is nothing but its effect in the output waveform. Will be more. So generally that's why we are trying to eliminate the lower order harmonics first. We are trying to eliminate the lower order harmonics first. Are you getting the point? Comparatively, suppose we are having the 99th harmonic. Suppose we are having the 99th harmonic. So for 99th harmonic, what is the value? It is a 4i0 divided by 99 pi na. You can check 4i0 by 99 pi. It will be very less value na, right? So we did not to worry much about the higher order harmonics. But for the lower order harmonics, we need to, yes, remove those harmonics. Okay, we need to remove those harmonics, right? Now, so this is about the IS expression, Fourier series expression of the sinusoidal current, Fourier series expression of the sinusoidal current, right? Sorry, not sinusoidal, it is a source current. It is a source current. Now, our main task is to find the input power factor. Okay, to find the input power factor, right? Next, now let me write fundamental component of the source current. Fundamental component of the source current. Yes. Fundamental component of source current. Yes. That is a IS1. IS. I am representing it with a IS1 is equal to what? IS at n is equal to 1. So it is a 4i0 divided by pi. 4i0 divided by pi into sine of omega t minus alpha. This is your IS1. This is the IS1. That is a source current at a fundamental frequency. That is a fundamental component we can say. Okay, 4i0 by pi into sine of omega t minus alpha. Now, what is the Vs we are having? We are having a Vs is a purely sinusoidal. Na? It is a Vm sine omega t. Okay. Also, Vs is equal to what? Vm into sine of omega t. Vs is equal to Vm into sine of omega t. Right? Now, can we find the distortion factor and displacement power factor in order to get your input power factor? Okay. So, how to find that distortion factor? So, distortion factor is equal to, yes, distortion factor we are having, it is a IS1 RMS divided by IS RMS. Na? What is the IS1 RMS? IS1 is this current we are having. So peak value is 4i0 by pi. So what is the RMS value? 4i0 by pi divided by root 2, na? Right? So let me write it as 4i0 divided by pi and whole divided by root 2. Is this clear? Right? So this is a 4i0 divided by pi divided by root 2. This is your distortion. Yes, IS1 RMS. And what is the IS RMS? If I want to find the IS RMS, so check the IS waveform, whatever we drawn here. Okay. This is IS. This is IS waveform. Yes, what is the RMS value of this waveform? It is I0 only, na? Yes or no? Right? Whatever the waveform running from alpha to 2 pi plus alpha, same will be repeating. Okay. Or from 0 to 2 pi, whatever the waveform we're having, the same will be repeating. So what is the RMS value? I0, right? Same we discussed earlier. So it is a I0. So you can check I0 will get cancelled out. So it is like a 2 root 2 divided by pi, na? 2 root 2 by pi. So if you check 2 root 2 by pi, it is equal to 0.9, na? 0.9. So this is your distortion factor. Distortion factor. Okay. Right? 0.9. Distortion factor. Next. Now, what is the displacement power factor? Next one is the displacement power factor. That is a DPF, na? Yes, DPF means what? It is a cosine of angle between VS1 and IS1. Now Vs is a pure sinusoidal, na? So can I say that this Vs is nothing but Vs1 only? Yes or no? Because Vs is a pure sinusoidal, the meaning is harmonic contents in the Vs waveform are 0. Is this clear? So that's why only fundamental component is present, right? So that's why Vs is nothing but Vs1. So it is a Vm sine omega t, and here it is Is1 is sine of omega t minus alpha. So what is the angle between these two? IS1 is lagging to VS na by angle alpha. Okay, so can I write it as cosine of angle between two means what? Cos of alpha. Cos of alpha, or you can write cos of minus alpha. You can write cos of minus alpha. But we know cos of minus theta is like your cos theta only. So it is a cos of alpha only. So this is your displacement power factor. So now what is the input power factor? Therefore, input power factor yes is equal to distortion factor into displacement power factor. No? So it is equal to 0.9 into cos alpha. This is your input power factor. Means for RL load as well as for RLE load. Okay. For single phase fully controlled bridge rectifier without a freewheeling diode, you can use this expression in order to get the input power factor. Okay, it is 0.9 into cos alpha, right? So this is actually the output of whatever we discussed till now, right? Very important expression. Number of questions they have asked, right? Next, so but this is valid only for this waveform of IS, na? Let me tell you, right? Only this waveform of IS. This is valid only for this. This is nothing but your 180-degree square wave mode. 180-degree. Why I am saying? You can check the pulse width alpha to pi plus alpha. It is 180-degree, na? So it is valid only for this waveform. If you are having IS is quasi square wave, right? And if you use this expression for input power factor, no, you will not get the marks, right? So for quasi square wave, again we need to derive the Fourier series expression. Are you getting the point, right? So this is for your single phase fully controlled rectifier only. Next, suppose we are having a single phase semi converter, then what to do? Let us discuss. Okay. I think shall we take a break, because it will be hardly 15 minutes remaining, and just we'll be starting the concept, and next we'll be we need to go for the break, right? So before, let us, shall I continue or shall we take the break? Because for that concept we require minimum 30 minutes. Okay, right? Okay. So we'll take a break here and we'll start at 7:05. Okay, 7:05, right? Okay. So now we're going to discuss the input power factor expression for single phase semi converter, okay, with RL load or RLE load, okay, but or highly inductive load, you can say. Input power factor RLE load in case of single phase semi converter. This is applicable for single phase semi converter as well as a single phase full converter RL load with a freewheeling diode. Okay, with the freewheeling diode also, right? So if you recall the IS waveform, right? IS waveform we're having, yes, it is like this source current waveform. Alpha to pi to pi plus alpha, pi plus alpha to 2 pi, and 2 pi to 2 pi plus alpha, right? The waveform is Cauchy square type, na, right? So alpha to pi, it is like this, I0, pi to pi plus alpha 0, pi plus alpha to 2 pi, it is a non-zero, that is minus I0, and again here it is 0. So 2 pi to 2 pi plus alpha 0 means here it is a 0 only, right? What is the magnitude? This magnitude is plus I0, and similarly this magnitude is a minus I0, right? Minus I0. Now, yes, this is the waveform we're having from 0 to pi, okay, 0 to 2 pi, 0 to 2 pi, right? Now, from this waveform, right, if you check whether it is a even or odd signal, this is neither even or not, okay, neither even nor odd signal, right? Because you can check before 0, again this cycle will be there, na, that is from 2 pi to pi plus alpha, whatever the cycle is there, okay, same cycle will be here from 0 till this instant, okay. This instant is like your pi minus alpha, okay. So it is like from 0 till this next pi minus alpha or minus pi minus alpha, it will be having negative cycle. So we can say that this is neither even nor odd signal. So in order to bring it into, do you want to say something? Hello, those who raised the hand.
No, sir.
We'll discuss it at the end, okay?
Okay, sir.
Okay. Please don't raise the hand. Okay. So now this is neither even nor odd signal, right? So in order to bring into the odd signal, what we need to do? Suppose if I shift this signal to the left hand side by alpha by 2 radian, I'm saying it now, alpha by 2 radian, okay, alpha by 2, then it will become an odd signal, okay. So how it will become an odd signal? Yes, let us see. I'm shifting this signal to the left side by alpha by 2. Alpha by 2 radian means instead of this alpha, now this will start at alpha by 2, na, okay. So from alpha by 2, right, till it was till pi, na, so it will be from instead of pi, now it will be till pi minus alpha by 2, okay, pi minus alpha by 2. So we'll be having the signal, let me write it as is dash signal, is dash signal omega t 0. I'm shifting this signal by alpha by 2, okay, or let me write it as alpha by 2 radian. Let us shift it at the left hand side. So it will be starting from alpha by 2. So it will be like this. Yes, this is your alpha by 2, okay. Next this will be like pi minus alpha by 2. Next here it is a pi plus alpha by 2, and next it will be like it was from pi plus alpha to 2 pi, na, right? So it is like 2 pi minus alpha by 2. 2 pi minus alpha by 2, and next will be the 2 pi. It is 2 pi. So the waveform will be like this. From alpha by 2 till pi minus alpha by 2 will be having this type. Next, here it is 0, here it is 0. Okay. Next, instead of this pi plus alpha, na, it will start from pi plus alpha by 2. Okay, pi plus alpha by 2. So it will start at this instant. Okay. And it will end, instead of this 2 pi, it will end at 2 pi minus alpha by 2. So 2 pi minus alpha by 2 means here. So what I have done, I have shifted the signal to the left hand side by alpha by 2 radian only, by alpha by 2. You can check here. What is the pulse width here? Alpha to pi means pulse width is pi minus alpha. Pi minus alpha means it is a pulse width. So in this case also you can check alpha by 2 to pi minus alpha by 2. So what is the pulse width? Pi minus alpha by 2 minus alpha by 2. So pi minus alpha by 2 minus alpha by 2 is again pi minus alpha. Yes or no? Right? Next you can check here the zero interval we are having. It is like pi minus alpha by 2 to pi plus alpha by 2. So it is like can we say that this is pi plus alpha by 2 minus in bracket pi minus alpha by 2, means this interval is for yes alpha radian only. Yes or no? Right? So you can check here also it is pi to pi plus alpha 0 na? Right? So same we are having waveform. The only thing is I have shifted this waveform to the left hand side. Okay. Now you can check before this omega t 0 means it is like omega t is equal to 2 pi. Okay. So before this instant, before 0, we'll be having which type of waveform? Yes, whatever the waveform we're having, from pi to 2 pi. This waveform will be, yes, this waveform will be getting, yes, before 0. So if we draw this waveform, whatever the waveform we're having from pi to 2 pi, yes, to the left side of the 0, then you can observe that the waveform is a odd signal, or the signal or the function is a odd function. Are you getting the point? Okay. So yes, here is dash. Yes, definitely this magnitude will be plus I0. This magnitude will be minus I0. Okay. So here is dash is a odd function. Is odd function or odd signal. Anything you can say. Now for any odd signal, we know an is 0. Okay, so therefore an is equal to 0. An is equal to 0, right? Next, what about the a0 by 2? That is the average value of this is dash. Average value of the is dash. You can check here pulse width. Here pulse width. Pulse widths are same only, na? Right? So what is the average value? Average value will be 0. Yes or no? Right? A0 by 2 is nothing but the average value of is dash. It is a 0. Okay. So yes, A0 by 2, which is equal to average of is dash, or average value of is dash, you can say, is equal to 0. Okay. So now we are having an is 0. A0 by 2 is also 0. Next, the thing is we need to find the bn. We need to find the bn. So how to find the bn? Yes. Bn is equal to, yes, we know it is a 2 by the periodic angle. What is the periodic angle? It is a 0 to 2 pi, whatever the waveform will be having. The same will be repeating from 2 pi to 4 pi. Okay. So it is a 2 by 2 pi. Integration from 0 to 2 pi. It is a is dash into sine of n omega t into d omega t. Right. So further we can write it as a 1 by pi. Now 0 to 2 pi, 0 to 2 pi, can we write it as alpha to pi minus alpha by 2, right? And from pi plus alpha by 2 to 2 pi minus alpha by 2. Okay, because these only were having the effective intervals, otherwise remaining intervals were having the 0 value. Okay, so let me write it as integration from alpha by 2 to pi minus alpha by 2, right? Alpha by 2 to pi minus alpha by 2. What is the value? I0. So it is a I0 into sine of n omega t into d omega t plus integration from, yes, you can check here, pi plus alpha by 2 to 2 pi minus alpha by 2. Okay, so it is pi plus alpha by 2 to 2 pi minus alpha by 2. What is value? Minus I0 na? Into sine of n omega t into d omega t, right? Now we need to simplify it. Can we take I0 outside common? Yes. So it is equal to I0 divided by pi into integration of sine. Integration of sine is minus cos. So it is a minus cos of n omega t divided by n, limit alpha by 2 to pi minus alpha by 2, right? Next, integration of sine is minus cos. This minus and minus cos, that will be plus. Okay. It is a cos of n omega t divided by n, limit pi plus alpha by 2 to 2 pi minus alpha by 2, right? So again, divided by n, we can take outside. Okay. So it is like I0 by n pi. Therefore, Bn is equal to I0 by n pi. Okay. Into, can we write it as, put the limit. It is like a minus cos of n pi minus n alpha by 2. Okay. So this is n here na. Instead of omega t, we need to put the limit. So n is there, right? So we can write it as a minus cos of n into pi, minus cos of n pi minus n alpha by 2. N pi minus n alpha by 2. This is the one thing. Plus we can write cos of n alpha by 2 plus cos of n alpha by 2. This is for one bracket. Similarly, we are in this bracket. It is a cos of 2n pi. Okay, 2n pi minus n alpha by 2. So plus cos of 2n pi minus n alpha by 2, minus n alpha by 2. Okay. And next thing is this term. Okay. Minus cos of n pi plus n alpha by 2, minus cos of n pi plus n alpha by 2, right? Now you can check. Yes, here cos of 2n pi minus n alpha by 2. You can check n is equal to 1. It is a cos of 2 pi minus alpha by 2. So what is the cos of 2 pi minus alpha by 2? Cos of 2 pi minus alpha by 2. It is same as that of your cos of alpha by 2 na. Similarly, you can put here n is equal to 2. It is a cos of 4 pi minus 2 alpha by 2. So what is the cos of 4 pi minus 2 alpha by 2? It is again cos of your alpha by 2. Okay, 2 alpha by 2 actually, right? So similarly, we can replace this bracket. We can replace this term. Okay, with I'm writing here, it is a cos of n alpha by 2. Cos of n alpha by 2. Now further we can write it as, which is equal to, you can check in calculator. Okay, cos of 2n pi minus n alpha by 2 for any value of n. Okay, for any value of n, you will be getting it is equal to cos of n alpha by 2 only. Okay, so it is a I0 divided by n pi into, it is like cos of n alpha by 2 plus cos of n alpha by 2. So it is a 2 into cos of n alpha by 2. This is the one term. Minus, this is a minus cos of n pi minus n alpha by 2 minus cos of n pi plus n alpha by 2. So I'm taking minus outside, and this can be written as, let me write it as, yes, cos of n pi plus n alpha by 2 plus cos of n pi minus n alpha by 2. Yes or no? I have taken minus common, and this term, yes, plus this term. So it is like cos of a plus b plus cos of a minus b na. Okay, so what is the cos of a plus b plus cos of a minus b? It is a 2 times cos a into cos b, right? So we can write it as, which is equal to I0 by n pi into 2 into cos of n alpha by 2 minus this as it is 2 times cos of n pi into cos of n alpha by 2 no? You can check cos of a plus b plus cos of a minus b. Okay, right? So it is 2 here, it is 2. Okay, so can we take these 2 common? Right, so it is equal to bn. Therefore bn is equal to 2 into I0 divided by n pi. 2 into I0 divided by n pi into, yes, cos of n alpha minus cos of n pi means what? It is again minus 1 to the power n, na? Right? So we can write it as cos of n alpha by 2, cos of n alpha by 2 minus, yes, n pi means minus 1 to the power n into this cos of n alpha by 2 as it is. Cos of n alpha by 2 as it is. Right? So further we can write it as 2 into I0 divided by n pi into cos of n alpha by 2. Okay. Into bracket 1 minus minus 1 to the power n. This is the expression of Bn. Now, in this expression, if you check for odd values of n, what this bracket will be? 1 minus minus 1 to the, you can check odd values. It is a minus 1 to the power 1, minus 1 to the power 3, minus 1 to the power 5, right? Minus 1 to the power 1, 3, 5, 7. If you check, it is a minus 1 only. So that minus this minus, it will become plus, means this bracket will become 2, na? These 2 and these 2, it will be 4. Okay. And for even values of n, means Bn will be non-zero, huh? For odd values of n. And for even values of n, what will happen? Minus 1 to the power 2. Minus 1 to the power 2 is plus 1. So this plus 1 and this minus, right? 0. Minus 1 to the power 4, you can check. Minus 1 to the power 6, you can check, right? So let me write this. Therefore, Bn is equal to 4 into I0 divided by n pi into cos of n alpha by 2. Okay, this is for odd values of n. Okay, and which is equal to 0 for even values of n. Okay, so Bn is equal to 0 for all even values of n. The meaning is, now if we want to write the expression of is dash, Fourier series expression. Okay, so we need to take summation over n is equal to only odd values, na? Because already a0 by 2 is 0, an is also already 0. The only thing is Bn we are having non-zero, and that too only for odd values of n. Okay, Bn is 0 for all even values of n, right? So therefore we can write, therefore is dash, this is a Fourier series expression, is equal to summation over n is equal to 1, 3, 5, 7 up to the infinity. Okay, only odd values. Okay, yes, what is the value? It is a 4I0 by n pi into cos of n alpha by 2. Cos of n alpha by 2. Okay, into, yes, this is the thing, into what? We are having some Bn sin of n omega t, na? Because you can check the Fourier series expression. We are having summation over n is equal to 1, 2, 3 up to the infinity. An cos of n omega t plus Bn sin of n omega t. So this is only Bn I have written. We need to write it as a sin of n omega t, right? This is the Fourier series expression of is dash. So now if this is the Fourier series expression of is dash, can we write the Fourier series expression for is now? You can check is we are having. Yes, this is the is dash. This is the is. So can we say that here is is lagging to is dash by angle alpha by 2, na? It is starting from alpha by 2. It is starting from alpha. So is is lagging to is dash by angle alpha by 2. Okay, so let me write. Yes, as is is lagging to is dash by alpha by 2 radian. So therefore, Fourier series expression okay of is is, yes, from this now we can modify. Okay, so therefore we can write is equal to same thing, summation over n is equal to 1, 3, 5, 7 up to the infinity. It is a 4 into I0 divided by n pi into cos of n alpha by 2. This is as it is into the here sin of, we need to write n into omega t minus alpha by 2, because IS is lagging to IS dash by how much angle? Alpha by 2. So that's what it is. Instead of omega t, we need to write omega t minus alpha by 2. This is your Fourier series expression of IS. Fourier series expression of IS. Now, with the help of this expression, yes, important thing. Okay, theoretical questions they have asked the source current. Okay, source current for L load, for highly inductive load. Okay, in case of your single phase fully controlled rectifier, and in case of your single phase semi converter, right? It consists of only odd harmonics, because you can check the IS expression we are having only summation over n is equal to 1, 3, 5, 7 up to the infinity. Na? Means only odd harmonics are there. For n is equal to 2, 4, 6, 8, 10, etc. We are having a zero value, na Bn value. So that's why only odd harmonics are present. Please note it. The source current, okay, for highly inductive load, okay, in case of your single phase fully controlled rectifier and single phase semi converter, it consists of only odd harmonics. It consists of only odd harmonics, right? So also sometimes they ask the questions like, suppose if your supply frequency is a 50 hertz, na, then what is the frequency of lowest order harmonic? So if you check, fundamental is not a harmonic, I have already told you. Okay, fundamental is your component. So after fundamental, your lowest harmonic present, lowest order present harmonic is third, na? And what is the frequency of third harmonic? It is a 3 omega. We discussed, right? As order of harmonic increases, its frequency increases, na? So frequency of the third is 3 times omega, na? So if source frequency is 50 hertz or fundamental frequency is 50 hertz, then your third harmonic frequency will be 150. 3 into 50, that is a 150 hertz. These type of questions also they have asked. Okay, so yes. Next, so this is your IS expression. Now we need to find the input power factor expression. So for that, we need to write the expression for DF and the DPF, na? Distortion factor and displacement power factor. Okay, so what is the distortion factor? Distortion factor. Yes, it is a ratio of IS1 RMS divided by IS RMS. Na? So before that, let us find the IS1 RMS. Yes, what is the IS1 RMS? IS1 is equal to, means what? IS1 means what? The source current at n is equal to 1. Na? Source current at n is equal to 1. Means here, if I replace this n is equal to 1, replace this n with 1, then we'll be getting it is a IS1. What is IS1? 4I0 by pi into cos of alpha by 2 into sine of omega t minus alpha by 2. Okay, so let me write IS1. Yes, 4I0 divided by pi into cos of alpha by 2 into sine of omega t minus alpha by 2. Omega t minus alpha by 2. This is your IS1, na? Right? So what is the peak value in this case? Peak value of IS1 means this bracket, this full term will be your peak. Sinusoidal function, na? So this indicates your IS1 peak. Yes or no? So what is IS1 RMS? Peak divided by root 2. So therefore, IS1 RMS is equal to IS1 peak divided by root 2. We know for any sinusoidal signal, any sinusoidal function, peak value divided by root 2 means your RMS value. Okay, so what is IS1 peak? 4I0 divided by pi into cos alpha by 2 and divided by root 2. If we do, it will be like 2 root 2 into I0 divided by pi into cos of alpha by 2. This is your IS1 RMS. Okay, IS1 RMS. Next, what is the IS RMS? You can check IS, we are having this type of waveform. This is IS. What is the RMS value of this? Yes, can we find the IS RMS? Yes. Next, IS, we are having this type of waveform. It is like from alpha till pi, pi plus alpha to 2 pi, right? So waveform is like this. This is the I0, and here it is a minus I0, right? So how to find the IS RMS? IS RMS. Now, this waveform is like you are having a half wave symmetry. So while finding the RMS value, either you can find over a half cycle or you can find over a full cycle, you will be getting the same answer. I am saying if we are having the waveform like this, which is having a half wave symmetry. Half wave symmetry means 0 to pi. Yes, whatever the waveform we are having, the same is there. Only thing is negative. Okay, so that is the half wave symmetry. So either I can find RMS value over the full cycle, that is 0 to 2 pi, or I can find the RMS over 0 to pi. In both the cases, you will be getting the same answer. Okay, so let me write it as, suppose over full cycle it is like this, 1 by 2 pi integration from alpha to pi na I0 square into d omega t plus integration from pi plus alpha to 2 pi. It is a minus I0 square into d omega t to the power 1 by 2. You can simplify either this or I am saying 1 by pi integration from alpha to pi I0 square into d omega t. You can simplify either this one or this one. You will be getting the same answer. Okay. So which is equal to, if you check, it is like under root, I'm writing directly pi minus alpha divided by pi. Okay. Into I0. This is your IS RMS, right? IS RMS. Next. So can we find now IS RMS? We know IS1 RMS. So can we find the distortion factor? Yes. So therefore distortion factor is equal to, yes, it is a IS1 RMS divided by IS RMS. IS1 RMS is this thing, 2 root 2 into I0 divided by pi. 2 root 2 into I0 divided by pi into cos of alpha by 2. This is your IS1 RMS divided by IS RMS is here, it is under root pi minus alpha by pi. Pi minus alpha divided by pi into I0. So if you simplify it, you can check here, this pi, sorry, 1 pi will get cancelled out. This is pi and this is divided by root pi, na? Right. 1 root pi will cancel out. I0 will get cancelled out. Okay. So it is like, yes, let me write this 2 root 2 into cos of alpha by 2, right? Divided by, this is like under root pi into pi minus alpha, na? Please check, this is divided by root pi and here it is a pi. So 1 root pi will get cancelled out. Only root pi will remain. That root pi I have shifted to this denominator side. So that's why under root pi into pi minus alpha. I0 will get cancelled out. 2 root 2 divided by this thing cos alpha. This is your distortion factor. Next, what is the displacement power factor now? Displacement power factor. So now displacement power factor. Displacement power factor, right? That is a DPF. It is a cosine of angle between fundamental source voltage and fundamental source current. Na? So what is fundamental source voltage? Vs is equal to Vs1 is equal to Vm into sine of omega t, because we are having a pure sinusoidal voltage. Na? So that's why only fundamental term will be present. And what is IS1? IS1 we are having this term. Yes, here it is. Okay. So 4I0 by pi into cos of alpha by 2. Into sine of omega t minus alpha by 2. Omega t minus alpha by 2. Right? Now you can check the phase angle. Okay. Or what is the phase difference between Vs1 and Is1? Yes. Here angle is omega t. Here it is omega t minus alpha by 2. Right? So therefore displacement power factor DPF is equal to what? Cosine of angle between these two, that is a minus alpha by 2, which is equal to cos of alpha by 2. Cos of minus theta is cos theta, na? Right? So it is a cos of alpha by 2. This is your DPF. So now therefore input power factor is equal to what? Your distortion factor into displacement power factor. What is the distortion factor? This is okay into this term, right? Into this cos of alpha by 2 we need to do. Okay, so it is a 2 root 2 into cos alpha by 2 divided by under root pi into pi minus alpha, right? Into, yes, this is thing df, and dpf is cos alpha into cos of alpha by 2. So if you take, yes, cos alpha by 2, cos alpha by 2, that will be cos square alpha by 2. Okay, so therefore input power factor is equal to 2 root 2 into cos square of alpha by 2 divided by under root pi into pi minus alpha. Is this clear? This is the input power factor for single phase semi converter. Okay, and as well as this is valid for single phase full bridge converter or the rectifier, RL load and with freewheeling diode. Okay, means when the source current is a quasi square wave na, at that time this expression is valid. Okay, so very important expression. Please note this at the very first page of your notebook. Okay, this expression and whatever the expression we discussed earlier, that is a 0.9 into cos alpha and this expression, right? These are very important expressions. Okay, so now we are going to discuss the numericals, right? So as long as your single phase rectifier is considered, only one point is remaining, that is the effect of source inductance. Okay, after that we'll be discussing about your three phase rectifiers, and the last one will be the dual converters. Okay, so yes, so let us discuss the numericals, right? Yes, suppose this question. Okay, so a single phase semi converter delivers power to RLE load with R is equal to 5 ohm, L is equal to 10 millihenry, and E is equal to 80 volt. The AC source voltage is 230 volt, 50 hertz. For a continuous conduction means what? Here, due to the inductor, your effect of E will not be observed in the V0, right? Means it is like your RL load only. It is like your RL load only. Okay. Find the average value of output current for a firing angle delay of 50 degree. And next, if one of the main SR is damaged and open circuited, find the new value of average output current on the assumption of continuous conduction. Okay, so let us discuss. Basically, they asked the two questions here, right? So let us first note the data. Yes, R is equal to 5 ohm. L is equal to 10 millihenry, which is equal to 10 into 10 to the power minus 3 Henry. E is equal to 80 volt. The AC source voltage Vs is equal to 230 volt. Frequency is 50 hertz. For a continuous conduction, this is important. Continuous conduction means your I0 waveform will not be having the zero intervals, right? I0 will be non-zero only for all the time, right? Next, find the average value of output current. So first thing is we need to find I0 average. Next, if one of the main SR are damaged and open circuited, find the new value of average output current on the assumption of continuous conduction. Here also we need to assume the continuous conduction. Okay, so we'll discuss that second question later on. So let us first concentrate on the first question. So RL E load we are having. Okay, continuous conduction they said, right? What is the expression of I0 average? Yes, what is the expression of I0 average in terms of V0 average and EMF E and resistor? Yes, RL E load continuous conduction. We are having the expression I0 average is equal to V0 average minus E by R na. right? Yes or no? Yes, V0 average minus E by R, correct? So now can we write? So in order to find the I0 average, I0 average is equal to V0 average minus E divided by R. Now in this case, E value directly given, right? R value we know. The only thing is we need to find the V0 average. Now you can check we're having a single phase semi converter. So if the single phase semi converter is there, then what is the V0 average? How will the waveform of V0 here? From alpha to pi, V0 will be same as of the supply voltage. Pi to pi plus alpha, whatever the V0, whether it will be having a negative pulse or it will be zero. Come on, speak out. It will be zero only, na, right? It will be zero only, right? So as it is a zero only, so can we write can we draw the V0 waveform? V0 will be like this, alpha to pi, right? Pi plus alpha, and after that the 2 pi here. So we'll be having the V0, this type of waveform. Okay. So here alpha to pi 1/1 diode will be in a conduction mode. Pi to pi plus alpha, if it is a symmetrical configuration, 1/1 diode conducts. If it is a asymmetrical configuration, both the diodes will conduct. Okay. So that's why the voltage will be zero. And during this interval, it is a Vs only. Na? So what is the V0 average for this waveform? It is a 1 by pi integration from alpha to pi Vm into sine of omega t d omega t. If we simplify it, we'll be getting it as Vm by pi into 1 plus cos alpha, right? 1 plus cos alpha. What is Vm? Whether they have given the Vm? Vs is given 230 volt. Na? So what is Vm? 230 into root 2 divided by pi into 1 plus, what is alpha? Alpha they have given, yes, 50 degree, na? Firing angle delay of 50 degree. So alpha is 50 degree. So it is a cos of 50 degree, right? So if you simplify it, we'll be getting V0 average. So therefore, V0 average. Yes, it is. How much? $170, na? Right? 170 volt. Right? 170.08, correct. So it is a 170 volt. This is the V0 average. But our task is to find the I0 average. Na? So I0 average is equal to V0 average minus E divided by R. So it is a 170 minus E is 80, na? And divided by R is 5. 80 and 5. So you can check it is 170 minus 80. So it is a 90, na? Yes, divided by 5. So how much it is? 18 ampere, right? Is this clear? Next, so this is the for first bit, very simple first bit. Second bit is interesting. So here in the second bit, the statement is if one of the main SCR is damaged and open circuited, find the new value of the average output current on the assumption of continuous conduction, right? So here try to understand the question. Yes, second bit I am writing, let me write it as a B here. So let us draw the circuit diagram. You can assume either it is a symmetrical or asymmetrical, right? Doesn't matter. Suppose I am assuming the asymmetrical, right? This is the Vs Thyristor is T1, T2. You can assume symmetrical or asymmetrical, right? Answer will be same in both the cases. D1, D2, R, L, and E. This is a V0 and I0. Now, yes, it is given that if one of the main SR is damaged and open circuited, okay. So suppose thyristor T2 is damaged and open circuited, okay. Suppose T2 is damaged and open circuited, okay. Means this thyristor is not working now. So how will be the V0 waveform? Can anyone? You can check at alpha. We are going to apply the gate pulse to thyristor T1. Alpha means Vs will be positive now. So thyristor T1 starts conduction. Along with T1, D2 will conduct. Current will flow from Vs, T1, load D2, and again back to the Vs. In this loop, current will flow. V0 will be equal to Vs only. This is till alpha to pi. After pi, what will happen? After pi, our inductor go on releasing the energy through D1, D2. So you can check. They have given the statement one more, that is on the assumption of continuous conduction. This is very important. What is the meaning of that assumption of continuous conduction? Means it is like our inductor is releasing the energy from pi till 2 pi plus alpha, because to thyristor T1 we are applying the gate pulse at alpha. After that, actually we are supposed to apply the gate pulse to thyristor T2, but whether T2 is working? No, T2 is open circuit now. T2 is damaged. So for thyristor T1 after alpha, when we are going to apply the gate pulse at 2 pi plus alpha, the meaning is as the conduction is continuous, the meaning is our inductor is sufficiently high so that our inductor is releasing the energy from omega t is equal to pi till 2 pi plus alpha, then and only then your continuous conduction is possible. Are you getting the point? And at 2 pi plus alpha, again thyristor T1 is turned on. Means actually our inductor is storing the energy only from omega t is equal to alpha till omega t is equal to theta or theta 1, you can say. RLE load is there now. So you can consider it as till theta or theta 1. But after that, our inductor is releasing the energy, okay, through D1, D2, okay. So first of all, from theta or theta 1, from theta 1 to pi, it will release the energy through D2 and T1. But after that, pi to 2 pi plus alpha, it will release the energy through D1, D2 only, right? Then and only then the continuous conduction is possible, right? So please, if you check the waveform of V0, how it will be? V0 waveform, if you want to draw at alpha, pi, 2 pi, and 2 pi plus alpha. Our thyristor T1 is okay. Thyristor T1 is functioning good, okay. But the problem is with thyristor T2. For thyristor T1, we are going to apply gate pulse at omega t is equal to alpha. So after alpha, yes, thyristor T1 and diode D2 will be in a conduction mode, okay. This will continue till your omega t is equal to theta, something theta, let us consider. Inductor stores energy. After theta till pi, inductor releases the energy through this thyristor and diode pair only, right? Recall the single phase semi converter, okay. So that's why here voltage is Vs only. And from pi till 2 pi plus alpha, okay, our inductor is releasing the energy through D1, D2 only. For this much of interval, that is for pi plus alpha, okay. This is pi to 2 pi, that is pi radian, and 2 pi to 2 pi plus alpha, that is again alpha radian. So it is a pi plus alpha radian. So during this interval, actually, inductor is releasing the energy through D1, D2. So what is the V0? V0 should be 0 now. So that's why it is a 0 here, right? And again at 2 pi plus alpha, same cycle will repeat. So here 2 pi to 2 pi plus alpha, whatever the waveform we're having, right? Same will repeat at 0 to alpha. Is this clear? The meaning is corresponding to negative half cycle of the supply na. Here in the output we are getting the 0 value only because your thyristor T2 is damaged. Okay, so let me write here from alpha to pi, which two devices will be in a conduction mode? T1 and D2. T1, D2 conducts. And from pi to 2 pi plus alpha, D1, D2 conducts. D1, D2 conducts. And what is this voltage? It is the same as that of Vs now. Is this clear? Right? Now this is the waveform we're having V0. So let me write here note, as conduction is continuous. Okay, as conduction is continuous, so therefore inductor L releases energy till 2 pi plus alpha. Okay, till 2 pi plus alpha, that is from theta 1 to 2 pi plus alpha, right? Next, otherwise your conduction will not be continuous. Okay, so now can we find for this waveform, can we find V0 average? Yes. So you can check whatever the waveform running from 0 to 2 pi, now the same is repeating from 2 pi to 4 pi. Okay, so therefore V0 average, therefore V0 average is equal to 1 by 2 pi integration from alpha to pi only, na, alpha to pi, it is a Vm sin omega t into d omega t. So if we simplify it, we'll be getting it as Vm by 2 pi into 1 plus cos alpha. So you can check which is equal to Vm is 230, na? So it is 230 root 2 divided by 2 pi into 1 plus cos of 50 degree. So if you check, it is equal to 85 volt, right? This is the V0 average. So now what is the I0 average? REL E load, na? So I0 average, therefore I0 average is equal to V0 average minus E divided by R, na? So it is 85 minus 80 divided by 5. It is a 1 ampere, right? This is your I0 average. Is this clear? I0 average is 1 ampere, correct? So okay, yes. Because they have given the continuous conduction, means even though your thyristor T2 is damaged, na, but as the continuous conduction is given, so continuous conduction is possible only when inductor will go on releasing the energy from just like your that theta, or you can say theta 1 till 2 pi plus alpha, then and only then it is possible, right? Next, yes, second question. A single phase bridge converter is used to charge a battery of 200 volt having an internal resistance of 2 ohm as shown in figure. Okay, it is a RE load actually. The SCRs are triggered by a constant DC signal. Yes, this is important statement. SCRs are triggered by a constant DC signal. What is the meaning of that statement? We are going to discuss. If SCR2 gets open circuited due to some fault, what will be the average charging current? Okay, that we need to find. So here you can check. This is a single phase fully controlled converter we are having, right? So RE load we are having, right? So let me draw here, or let me first note the data. E is given, it is a 200 volt. R is equal to 2 ohm. Yeah, SCR2 is open circuited, right? Supply voltage is given 230 volt. Frequency is a 50 hertz. Yeah. Right. So now our task is to find the average charging current. That is nothing but I0 average. This is I0 suppose. Our task is to find average charging current, means I0 average only. Okay. So now here, yes. Okay. So single phase fully controlled rectifier with RE load, we know omega t. This is a Vs. Suppose Vs waveform is like this, 0 to pi, right? Pi to 2 pi, 2 pi to 3 pi. And E we are having, suppose this type of E. Suppose this is theta, it is pi minus theta. Okay, and also we considered the mirror image of this one. Recall whatever we discussed in the yesterday's session, right? This is like your pi plus theta, and it is like your 2 pi minus theta, no? And similarly, this is 2 pi plus theta, and so on, right? So now please try to understand this statement. SCRs are triggered by constant DC signal. This is very important statement. SCRs are triggered by constant DC signal. I am writing here. SCRs are triggered by constant DC signal. Means here your gate current, okay, is a constant. Gate current is a constant. So suppose if the gate current is constant, let me write here. Yes. Let me show here. Gate current is a constant. This is omega t and this is Ig. This is the constant gate current, right? Means for all the 4 SCRs, okay, for all the 4 SCRs, I have applied the gate signal, okay, this type of waveform, that is a constant gate current. Now my question is, if you check the Vs and E waveform, if you check the Vs and E waveform, at which instant T1 and T4 will conduct? If we check this Vs and E waveform and this gate current waveform, my question is at which instant, because they have not given the firing angle, but indirectly they have given the firing angle, right? They have given the constant gate current now, that is a constant firing signal, right? Constant firing signal, constant DC signal. Okay, the meaning is as soon as our SCR, respective SCR will be in a forward bias mode, that SCR will immediately start conduction. You can check. Suppose that for all the 4 SCRs, I have given the gate signal at omega t is equal to 0, right? But we know after omega t is equal to theta, okay, that is from theta to pi minus theta, we will be having SCR1 and SCR4 in a forward bias mode. Na? You can check here SCR1, SCR4. These two will be in a forward bias mode during which mode? During theta to pi minus theta. Before theta, you can check before theta SCR1 and SCR4 are in a off state, na? Right? Because they are in a reverse bias mode. So even though we have applied the gate signal, but SCR1 and SCR4 are in a reverse bias mode during 0 to theta. So whether our SCR1, SCR4 will turn on between 0 to theta? No. They SCR1, SCR2, SCR1 and SCR4 will start turning, will start conduction only at omega t is equal to theta. That is from theta till pi minus theta. Our SCR 1 and 4 will be in a conduction mode. Is this clear to all? Are you getting the point? Means even though we applied the gate signal like this, but before triggering or before turning on, yes, what is the requirement? SCR should be in a forward bias mode. Na? If SCR is in a forward bias mode, then and only then your junction J1, J3 forward bias, junction J2 reverse bias. Okay. So after theta only our SCR 1 and 4 are switching into the forward bias mode. And due to that, at this instant, our SCR1 and SCR4 will, yes, turn on at this instant. And from here till here only, SCR1 and 4 will be in a conduction mode. Yes or no? Right? Next, because after pi minus theta, again Vs is less than E. So our SCR1 and 4 will be again in a off state. Okay. So now, if we want to draw the V0 waveform, how it will be? You can check V0 waveform. It is theta. This is a pi minus theta. This is a pi. Okay. Let us first discuss only till pi. After pi, what will happen? Let us discuss. After this interval, pi minus theta, and this is theta. Okay. So as I said, during theta to pi minus theta, SCR1 and SCR4 are in a on state. Okay. So SCR1 and 4 are in a conduction mode means what? It is like a plus here, minus here. Current will flow from Vs, SCR1 load, SCR4 and again back to the Vs like this. So what is a V0? That is a voltage across load is equal to Vs only, na? Right? So let me draw voltage across load waveform. It is same as that of the Vs. Before that, what is the V0? Before theta, what will be the V0? Yes, before theta, what will be the V0? Okay, some are saying 0, some are saying E. You can check na RE load we are having. For RE load, if load current is 0, then what is the V0? It is a E only na, because load is a RE. So that's why V0 is equal to E, right? So we'll be having the V0 is E here. Is this clear? From theta to pi minus theta, V0 is equal to Vs. Okay. So now you can check at E, Vs and E both are same. At theta, Vs and E both are same. At theta, Vs and E both are same. After that, Vs is greater than that of E, right? So our thyristor will 1 and 4 are in a conduction mode. So that's why we'll be getting V0 will be same as that of the supply voltage. So we'll be getting this type of waveform. At pi minus theta, again both are same. Okay, so pi minus theta to pi, it is a constant only. It is a constant only. So this is your Vs, this is the E, this is the E, right? Next, after pi, what will happen? After pi, supply voltage is negative na? After pi, supply voltage is negative means after pi, supply voltage negative means minus here plus here. Okay, but you can check thyristor T2 na, SCR2 is damaged. Okay, it is a faulted and open circuited. So now my question is, even though at pi plus theta, your SCR2 and SCR3 will be in a forward bias mode, but as SCR2 is in an open circuit mode, it is a damaged. So what will happen to the circuit operation? Pi to pi plus theta, definitely it will be E only, because during pi to pi plus theta, your SCR2 and 3 will be in a reverse bias mode. Okay. Now at pi plus theta, what will happen? After pi plus theta, you can check Vs is greater than E. But SCR2 is a damaged na. So that's why SCR2 is an open circuit. So what will happen? Whether the current will flow through SCR2 supply, SCR2 load, SCR3 and again back to the supply. Whether the current will flow in this loop? No, current will not flow. The meaning is what? Current during this interval na, that is from pi plus theta to 2 pi minus theta, the current will be, this is 2 pi minus theta. Current will be 0. So what is the V0? V0 is equal to E only na, right? Actually, if suppose SCR2 is not damaged, in that case, how will be the waveform? If it is not damaged, then the waveform will be pi plus theta to 2 pi minus theta. Waveform will be same as of the supply voltage. But as SCR2 is damaged, okay, so that's why it will not conduct at all. Okay, so due to that, output current will be 0 only. Current will not flow from source towards the load. So that's why we will be getting the E only. Output voltage is E only. This will continue till 2 pi minus theta. From 2 pi minus theta to 2 pi, what will happen? Yes, from 2 pi minus theta to 2 pi, what will happen? Again, your SCR2 and 3 will be in a reverse bias mode na, because Vs is less than E. Mod Vs is less than E. So that's why we'll be getting again, it is a E only. We'll be getting E only, right? And after 2 pi again, the same cycle repeats na, right? So this type of waveform will be repeating again. Okay, so we'll be getting again this type of waveform, right? Now this is the V0 we are having. Now what about the I0 waveform? Yes, how will be the I0 waveform? Yes, can anyone? I0 waveform. Zero to theta, theta to pi minus theta. Okay, 0 to theta, theta to pi minus theta, pi minus theta to pi, right? Pi to till 2 pi, we're having this type. Okay, so I0 waveform will be 0 to theta. What is I0? 0 to theta, what is I0? Come on, speak out. 0 to theta, I0 will be 0 only, right? I0 will be 0 only. Yes or no? Because thyristors are in a reverse bias mode. Okay, so that's why here 0. Theta to pi minus theta, I0 is Vs minus E by R, na? Right? So it is a Vs minus E by R. Check the waveform. pi minus theta to pi, it is a 0 only, because you can check Vs is less than E na, Vs is less than E. And after that, thyristors are not in a conduction mode till 2 pi na. So output voltage is only E. That's why here your current will be 0 only till 2 pi. So we are having this type of waveform in the I0. After 2 pi, again the same cycle will repeat. Right? So now, can we find the I0 average here? Why I have drawn the I0 waveform? By using this waveform also V0, we can first find the V0 average, and after that we can find the I0 average. But here we require first intervals 1, 2, and 3 intervals, right, to simplify. But whereas here only one interval is sufficient, or one integration is sufficient. Okay. So how to find I0 average? I0 average is equal to 1 by 2 pi integration from theta to pi minus theta. It is a Vs minus E divided by R into d omega t. So you can check it is equal to 1 by 2 pi integration from theta to pi minus theta. Vs is Vm sin omega t na, minus E divided by R into d omega t. Now can we simplify it? Yes. So it is 1 upon 2 pi R. Therefore I0 average 1 upon 2 pi R into, it is a Vm into, yes, Vm into integration of sine is minus cos of omega t. Limit theta to pi minus theta. Yes, minus E into omega t na. Limit theta to pi minus theta, right? Is this clear? So which is equal to 1 upon 2 pi R into Vm into, we can write it as a minus cos of pi minus theta, minus cos of pi minus theta plus cos theta, minus E into pi minus theta minus theta na? So which is equal to 1 upon 2 pi R into Vm into cos of pi minus theta. It is a minus cos theta na, right? So it is minus cos theta and this cos theta. That is minus of minus cos theta. That is cos theta plus cos theta, 2 cos theta. 2 Vm into cos theta minus E into pi minus 2 theta. Now in order to find the value of I0 average, we need to find the theta na. How to find theta? Come on. Theta is equal to what? Sine inverse of E by V max na. Because at omega t is equal to theta, supply voltage and E both are same. Okay. So next we can write at omega t is equal to theta, Vs is equal to E. So Vs means Vm sin theta, which is equal to E, right? So therefore we can write theta is equal to sine inverse of E upon V max. So you can check it is a sine inverse of, what is E? 200 na? 200 divided by V max 230 root 2. Okay. So it is equal to 37.94 na degree. This is theta. Correct? Now if this is the theta, can we find the I0 average? Yes, I0 average is equal to 1 upon 2 pi R. Yes, what is R? 2 ohm na? Yes, into 2 into, just a minute. Yes, here it is. 2 into Vm into cos theta. Let me write here 2 into Vm 230 into root 2 into cos of this angle 37.94. correct? Next, minus E. E means 200 into pi minus 2 theta. No? It is a pi minus 2 into, now theta we need to put here in radian, no? Because it is pi minus, right? So theta is 37.94 into pi upon 180. Yes, please simplify it and check the value of I0 average, right? Okay. One announcement is there. Those who have completed the digital subject, I think it is a digital electronics, right? They will be having a test on 11th September from 4 to 4:40, 4 to 4:45. Okay. Yes, what is the I0 average? Why this is root 2? Because this 230 volt they have given, na, it is the RMS value of the supply. And we require here peak value, na, VM. So that's why it is a RMS into root 2 means peak value, right? Okay. Yes, 11.9, na? 11.925, right? Okay. 11.925 ampere. So this is your I0 average. Is this clear? This is the I0 average. So if you check the options, 11.9 ampere, option C is the correct option, right? Okay. So here we need to understand the SCR2 is open circuited here, right? So how is the waveform of I0? How is the waveform of your V0? Whereas in the previous question, it was the RLE load, but they stated that it is a continuous conduction, right? So, next, let us discuss the next question. Okay, so this one, this is simple question. A single phase semi converter is operated from a 50 hertz 240 volt AC source. If a resistive load of 100 ohm is connected at the DC terminals of the converter and the average output voltage is 25% of maximum possible average output voltage, calculate the firing angle, average and RMS load currents. Okay, our task is to find the firing angle and the average load current and the RMS load current, right? So let us first note the data. Single phase semi converter, supply voltage is 240 volt, frequency is equal to 50 hertz, resistive load R is equal to 100 ohm, is connected at the DC terminals of the converter, and the average output voltage, that is V0 average, is equal to 25% of maximum possible average output voltage. Okay, so 25 means 25% means 25 by 100 into V0 average, or let me write it as maximum V0 average. Okay, max V0 average. Right. Next, our task is to find the alpha average and RMS load current, I0 average and I0 RMS, right? So this thing we need to find, correct? So now my question is, what is the value of alpha for getting maximum V0 average? Single phase semi converter we are having, it is a purely resistive load. Okay, very simple circuit, right? So our waveform will be like from alpha to pi. Okay, for omega t is equal to alpha to pi, V0 is equal to Vs, pi to pi plus alpha 0, pi plus alpha 2 pi, again it is a Vs. Okay, so this type of waveform will be getting. But in order to get the maximum V0 average, what is the alpha value? 0, na? Right? Alpha should be equal to 0. Correct? Alpha should be equal to 0. Okay. So, okay, good. So please check. Yes. Semi converter with R load we are having. So waveform will be like this. Alpha pi plus alpha 2 pi. Okay. We'll be getting this type of waveform. Right? So your V0 average, you can check if alpha reduces, na, if alpha reduces, the area under this curve, it increases, na. So if alpha is 0 degree, yes, maximum area you will be getting. Okay. So for maximum V0 average, alpha is equal to 0. Okay. So let me write for maximum V0 average, firing angle alpha is equal to 0 degree. So now can we write it as V0 average for the given, yes, waveform, it is equal to 1 by pi integration from alpha to pi Vm into sine of omega t into d omega t, na? So which is equal to Vm by pi into 1 plus cos alpha, right? This is your V0 average. So therefore maximum V0 average means what? V0 average at alpha equal to 0 degree. Okay. So next, maximum V0 average is equal to V0 average at alpha equal to 0 degree, right? So what is V0 average? Vm by pi into 1 plus cos alpha. So it is Vm by pi into 1 plus cos alpha means 0, na? 0 degree. So it is like 2 Vm by pi. So you can check it is a 2 into, what is Vm? 240 into root 2, na? RMS value is 240. So maximum value will be 240 into root 2 divided by pi. Yes, how much? 2 into 240 into root 2 divided by pi. 216.07 volt. Okay, this is your maximum V0 average. But we require the 25%, na? You can check. Our V0 average is 25% of this maximum V0 average. Okay, so therefore V0 average, is equal to 25% means 25 by 100 into maximum V0 average. So you can check it is a 0.25 into 216.07. So if you check it is equal to 54.0175 volt. Okay, this is the V0 average. Is this clear? Now this is the V0 average we are having. Our task is to find alpha, I0 average and I0 RMS. Okay, so how to find the alpha value? We know V0 average expression is 2 Vm by pi into cos alpha, na? Vm by pi into 1 plus cos alpha, right? So now, yes, as V0 average is equal to Vm by pi into 1 plus cos alpha. So V0 average is 54.0175 is equal to 240 into root 2 divided by pi into 1 plus cos alpha. So from this, can we find alpha? Yes. Please check and find the alpha value. Alpha is 120. Some are saying 60, some are saying 120. Please check once. 120, right? Alpha is 120. Okay. Correct? Alpha is 120 degree. $60 or 120? 54.0175 into pi 240 root 2. It's a 60 degree, na? $90 degree. Okay. It's a 60 degree. Yes or no? We need to find cos alpha and then we need to take the cos inverse. Multiply this term, divide here. This term 1 minus this term we need to do. Okay. Just a minute, just a minute. I think it is 120, correct. But this will be -1, na? Yes. Yes, 120 degrees, correct, correct. 120 degree. Please check once. 120 degree, because it will be cos inverse of -0.5, right? So 120 degree. Next, so this is alpha. This is the alpha. Now our task is to find the I0 average and I0 RMS. How to find I0 average? I0 average is equal to purely resistive load. So it is V0 average by R divided by R, right? So if you check, it is equal to V0 average, we have written 54.0175 divided by resistance value is 100, na? 100. So it is like a 0.5402 ampere, correct? I0 average. How to find I0 RMS? So for that we need to find V0 RMS. Okay. V0 RMS is equal to 1 by, you can check this waveform, right? We need to find the RMS value of this V0. So it is a 1 by pi integration from alpha to pi. Vm square into sin square of omega t into d omega t to the power 1 by 2, na? So if we simplify it, we'll be getting it as Vm upon root 2 pi into, it is like a pi minus alpha plus sine of 2 alpha by 2 to the power 1 by 2, right? So it is 240 into root 2 divided by root 2 pi into pi minus alpha. So alpha means this is the subtraction, okay, arithmetic operation of angles. Okay, so it is a pi minus alpha. We need to put in it in radian, na? 120 degree means it is a 2 pi by 3, right? Plus sine of 2 into 120 divided by 2 to the power 1 by 2, right? Please simplify this and find the RMS value, right? V0 RMS. Yes. What is V0 RMS? $106.11. correct? 106.11. Okay. Okay. Is this okay? 106.11, correct? 106.11. So V0 RMS is equal to 106.11. So therefore V0 RMS 106.11 volt. Okay. Here I have written 2 pi minus 2 pi by 3, na? Because our alpha is 120 degree and 120 degree to its radian equivalent is a 2 pi by 3, na? Or you can write 120 into pi by 180. Okay, you will be getting it as a 2 pi by 3 only, right? Okay. So this is V0 RMS. I0 RMS is equal to V0 RMS by R. So if you check, it is equal to 106.11 divided by 100, na? 1.0611 ampere, right? This is your I0 RMS. Final answer. Correct? No, alpha is 120 degree. Abhinandan. Correct? Okay. Right. So let us discuss the next numerical. Yeah, this is somewhat different. Okay, so the input voltage given to a converter is V is equal to 100 root 2 into sine of 100 pi t volt. The current drawn by the converter is, they have given 10 root 2 into sine of 100 pi t minus pi by 3 plus 5 root 2 into sine of 300 pi t plus pi by 4 plus 2 root 2 into sine of 500 pi t minus pi by 6 ampere. The active power drawn by the converter is, okay, means we need to find the real power, that is the power P. Our task is to find the power P, right? This is the one question, and one more question they are asked on the same data. Okay, so here it is. Question number 13 is the second question. Input power factor of the converter is, so our task is to find the input power factor and the active power, that is the real power drawn by the converter. Okay, so yes, so in this case, if you check, they have given V is a, that is a voltage to the converter is 100 root 2 into sine of 100 pi t. The meaning is voltage is a pure sinusoidal because it is having only sine of 100 pi t term. Okay, means the harmonics are not present. It is a pure sinusoidal voltage they have given. The current drawn by the converter is, you can check, this is frequency is 100 pi. Here frequency is 300 pi. Here frequency is 500 pi. The meaning is, in the current we are having a fundamental component, third harmonic component, and the fifth harmonic component. Is this clear? So in the voltage we are having only fundamental component, but whereas in the current we are having a fundamental component, third harmonic component, and the fifth harmonic component. Our task is to find the active power drawn by the converter. Okay, now how to find the active power? So active power means what? It is a V into I into cos phi. But in this case, if you check, the converter is having only fundamental component of the voltage. In the voltage, we don't have the third harmonic, fifth harmonic component. We have only fundamental component. So in the voltage at the third harmonic and the fifth harmonic component is not there. Okay. So what is the product of third harmonic component of voltage and the third harmonic component of the current? It is a zero only. Yes or no? Means as here current is having only fundamental component, in order to find the active power, we need to consider only the fundamental component of the current. We need to consider only the fundamental component of the current, right? Because in the voltage, third harmonic and fifth harmonic components are not there. Okay. So now how to find the real power? Let us discuss. So first bit, that is question number 12. V is given, it is equal to 100 into root 2 into sine of 100 pi t. 100 root 2 into sine of 100 pi t. Okay, this is only V1 because only one component they have given. Okay, and you can check this frequency is 100 pi, and here also current is having a frequency of 100 pi t. That is a fundamental component of current, and this is like a fundamental component of voltage, right? This is a fundamental component of voltage. Now let me write I is equal to given 10 root 2 into sine of 100 pi t. 10 root 2 into sine of 100 pi t. Okay, minus pi by 3. Minus pi by 3. This is the one thing. Plus 5 root 2 into sine of 5 root 2 into sine of 300 pi t plus pi by 4. 300 pi t plus pi by 4 plus 2 root 2 into sine of 500 pi t plus, sorry, minus pi by 6. This is a current. Okay, so let me write current has fundamental component third harmonic component and fifth harmonic component. But voltage has only fundamental. Okay, as voltage has only fundamental component. Only fundamental component. Okay. So therefore, what is the real power or the active power due to the third harmonic component and the fifth harmonic component? As the voltage is not having third harmonic and the fifth harmonic component, so the active power of the third harmonic component and the fifth harmonic component will be 0. Okay, so voltage has, yes, voltage is not having third harmonic and fifth harmonic component. Third harmonic and fifth harmonic component. So therefore, active power of third harmonic and fifth harmonic, third harmonic and fifth harmonic component is equal to 0. Okay, so for the question number 12, the active power means only fundamental component active power. Okay, so now active power is equal to only fundamental component active power. Only fundamental component active power. Active power, right? So how to find the fundamental component active power? We know na, in AC circuit, what is the active power? V into I into cosine of angle between V and I, right? But that is when your current and voltage both are sinusoidal. Okay, that is yes, both are sinusoidal and are not having any harmonics, right? But here also we have considered only fundamental, right? So that's why here we need to write VS1. It is a V1 or VS1 they have given. It is a V they have given. Okay, so let me write it as V1 RMS into I1 RMS into cosine of angle between V1 and I1. Cosine of angle between V1 and I1. Is this clear? cosine of angle between V1 and I1. So you can check V1 RMS is, how to find V1 RMS? V is nothing but V1 na, only fundamental component. So peak value is 100 root 2. So what is RMS value? 100. Yes or no? 100 root 2 by root 2 means what? RMS na, peak by root 2. So it is 100. Into what is the I1 RMS? You can check fundamental component is this one na. So it is 10 root 2 is a peak value. So peak divided by root 2 means RMS, that is a 10. Into what is the angle between I1 and V1? Here V1 is 100 pi t. I1 is 100 pi t minus pi by 3 na? That is a 60 degree. So angle between these two is 60 degree. So it is into cos of 60 degree. So you can check it is 100 into 10 into cos 60. I think it is 500. Right? 500 watt. This is your active power. Is clear?
Hello.
Yes.
Good evening, sir. Sir, in this question, why you have not taken the product of the first fundamental component and third harmonic? Like, why is it 0 the power?
Because you can check while finding the power. Okay. Your frequency of the fundamental is 100 pi.
Yes, sir.
Frequency of the third is 300 pi.
Yes, sir.
So we cannot find the power different frequencies, two quantities with the different frequencies, right?
Sir, but if we multiply two sinusoidal signals, then we will get some expression. So can't we solve it and
No, we can't use that actually.
Okay.
We need to only find the fundamental power, third harmonic power and fifth harmonic power.
Okay. Sir, one
So
more doubt.
if the voltage is also having the third and the fifth harmonic na,
Okay.
then we could have calculated the third harmonic as well as fifth harmonic.
So, sir, we have to find the corresponding multiplication of the fundamental component, third harmonic and fifth harmonic.
Yes, correct.
So, if the total power is given, like in voltage, if there are third harmonic and fifth harmonic also,
Then
so,
your total power will be equal to P1 plus P3 plus P5.
Okay, sir, got it.
Right?
Sir.
That I will tell you because they have given one note also at the end.
Yes, sir.
Yes.
Sir, one more doubt. Sir,
Yes.
generally RLE load is like DC motor, na? So, like for the EMF generated by DC motor, back EMF is basically P phi NZ by 60A. So, phi basically flux depends on the voltage that is getting applied. So, since the input voltage is continuously changing, so how can we consider that back EMF is constant? Because phi will also change na, according to the input voltage.
No. Actually, the thing is here while doing the analysis, we are assuming that E is a constant.
Okay.
Right? Here, if you analyze, if you consider the E is variable, na, then
Yes.
you cannot analyze here.
So, sir, but in DC motor, what will happen? The E will be constant practically, or it will vary along
It
with
depends
the...
on actually if you check the DC motor, EB is equal to your 5P ZN divided by 60A, na?
Yes, sir.
So it is proportional to your flux phi.
Yes, sir.
And proportional to speed something, right?
Yes, sir.
Okay, so it depends. Means if your motor is supplying the variable speed load, na,
Okay.
then accordingly your EB also changes. Again, it depends if you are having the separately excited motor, and if suppose that separately excited motor, that field winding is connected to the external source, separate source, and if that source is a constant, na, then your flux will be constant.
Yes.
Then your EB will be directly only depends on your speed, right?
Yes, but sir, in a single phase full wave rectifier, we have got input is varying, it is sinusoidal. So along with it, the flux is also getting sinusoidal only.
Voltage input is sinusoidal, but its RMS value is fixed, na?
Yes, sir. Yes, sir.
So think in that way.
Okay, sir.
It is not like that voltage is sinusoidal, means whatever the output voltage you are getting. Again, it is not like that whatever the actual output you are getting in a waveform. That
sir.
waveform I am not directly giving as an input to the motor.
Yes,
In
sir.
between, we are having the filters also in order to maintain the constant voltage.
Okay, sir.
Right?
Got it, sir. Thank you, sir.
So we'll discuss the remaining doubts at the end. Okay. Otherwise, it will be disturbing the class. Right. Okay. So this is active power is 500 watt. Right. Next, the second question they asked. Yes. The input power factor of the converter is. Okay. Our task is to find the input power factor of the converter. Now you can check here. Input power factor is equal to what? It is a dpf into df na. We have written IPF, input power factor, is equal to displacement power factor into distortion factor. So first thing is we need to find the distortion factor. Next we need to find the displacement power factor, and then we need to take the multiplication, right? So let me write here. Yes, input power factor, I think question number 13. Input power factor is equal to distortion factor into displacement power factor. Okay, so how to find distortion factor? Distortion factor is equal to IS1 RMS na, divided by your IS RMS. Now instead of IS, I think they have used the notation like I only na. Yes, it is a I. So let me write it as I only. Instead of IS, let me write it as I. I1 RMS and I RMS. Right? So now we need to find I1 RMS and I RMS. So what is I1 RMS? You can check the current expression they have given. Yes, it is a fundamental is peak value is 10 root 2 na. So RMS is equal to 10 ampere. Okay, so it is a 10 ampere. Is this clear to all? I1 RMS is 10 ampere because your I1 1 stands for fundamental, subscript 1 stands for fundamental. Okay, so that's why here you can check. This is your instantaneous value of the fundamental component current. So peak value will be 10 root 2, RMS value will be 10 root 2 by root 2. So that's why it is a 10 only, right? So that's why here I have written I1 RMS is 10. How to find the IRMS? Now how to find the IRMS? Keep it in mind. If you are having the current expression or any sinusoidal, suppose they have given the expression of the alternating quantity which consists of different harmonics now, then how to find the total RMS current? Okay, it is like under root. It is like a under root of RMS of the fundamental square, RMS of the third harmonic square plus RMS of the fifth harmonic square. Okay, so let me write it as it is equal to under root I1 RMS square plus I3 RMS square plus I5 RMS square. Okay, means we need to take the square. We cannot directly add a I1 RMS plus I3 RMS plus I5 RMS because the frequency of your fundamental third and fifth, whether they are same, no, frequencies are different. So that's why while finding the total RMS na, we need to write, yes, we need to write in this way, right? So that's why I1 RMS square plus I3 RMS square plus I5 RMS square. So now I can write it as this is I5, it is not IS, it is a I5. Now can we write it as IRMS? Therefore, IRMS is equal to under root. What is the I1 RMS? It is a 10, 10 square. Plus you can check I3 RMS. It is a 5 root 2 by root 2 na. 5 root 2 is a peak value. So it is a 5 square. And what about the I5 RMS? It is a 2 root 2 by root 2. So it is a 2 square, right? So it is a 2 square. So you can check it is equal to under root 100 plus 25 plus 4, that is under root 129. No? 11.358. Right? This is a ampere. This is your IRMS. So now what is the distortion factor? Distortion factor is equal to 10 upon this term, no? 11.358. So if you check, it is equal to 0.88, 0.88. This is your distortion factor, right? Now what is the displacement power factor? It is equal to cosine of angle between VS1 and IS1 na? VS1 and IS1. So we can write it as cos of, what is the angle between VS1 and IS1? It is a 100 pi t, it is a minus pi by 3. So it is a 60 degree, cos of 60 degree. So if you check, it is a 0.5. This is your displacement power factor. So what is input power factor? So therefore, input power factor is equal to DF into DPF. So it is equal to 0.88 into 0.5. Na? I think it is a 0.44. This is the input power factor. Is this clear? Right? So this is the answer for the question number 13. Next, they have given one note also. Yes, here it is. If the voltage has third harmonic component also, then how to find PS and power factor? Okay. If the voltage also, if the voltage having the third harmonic component, means voltage is not having the fifth harmonic now. Okay. Voltage is having the third harmonic. Then how to find the power P, active power? Yes, that is the apparent power and the power factor. Okay. So let us discuss. So next, if the voltage is also having if the voltage is also having fundamental and third, okay, fundamental and third harmonic component, means now the case is like voltage is having a fundamental and third harmonic and current is having a fundamental third and fifth harmonic. Okay, then how to find the power, active power, apparent power, and your input power factor? Okay, that we'll discuss. Okay, so here you can check here, if voltage is also having the fundamental and the third harmonic, then your voltage V, okay, that is the RMS value of the voltage V. Okay, let me write it as V RMS is equal to V1 RMS square into I1 RMS square. Sorry, not I1 RMS. V1 RMS square plus V3 RMS square plus V3 RMS square. If you simplify it, we'll be getting V RMS. How to find IRMS? We already discussed. It is equal to under root I1 RMS square plus I3 RMS square plus I5 RMS square. Okay, so it will give you the IRMS and VRMS. Okay, VRMS and IRMS, right? Now how to find the power P? So first, how to find the S? S is equal to your VRMS into IRMS directly. S is equal to VRMS into IRMS, right? How to find the active power P? Yes, active power P is equal to, now you can check, voltage is having a fundamental and third, current is having a fundamental third and fifth, voltage is not having the fifth harmonic, so that's why the active power corresponding to the fifth harmonic will be 0. The only thing is there will be the active power due to the fundamental and active power due to the third harmonic na? So it is equal to P1 plus P3. How to find P1? How to find P1? P1 is equal to, yes, it is a V1 RMS into I1 RMS into cosine of angle between the two. Okay, cosine of angle between the V1 and I1, cos of angle between V1 and I1. This is the one thing. Plus, similarly, we will to find V3 RMS. This is actually P1, right? Let me write P3. V3 RMS into I3 RMS into cosine of angle between V3 and I3. So this will give you the P1, this will give you the P3, and P1 plus P3 means the P, right? And how to find the input power factor? That is the power factor. Now power factor is equal to P upon S, right? This will give you the power factor. Is this clear? Right? So please keep it in mind. If the voltage is having a harmonics, then it is total voltage RMS value is equal to under root V1 RMS square plus V3 RMS square. If the fifth harmonic is present, then it will be plus V5 RMS also. We need to add current. How to find RMS? Right? We discussed the total power P is equal to fundamental power plus third harmonic power. Fundamental power is V1 RMS I1 RMS into cosine of angle between V1 I1. Third harmonic power is equal to V3 into I3, that is RMS value, into cosine of angle between V3 and I3. Right? Okay. So yes, need to be multiplied by 3. No, yes is not required to multiply by 3. Right? Okay. Okay. So yes. So this is your power factor. Next, let us discuss the next question. This is actually related to your source inductance. We'll discuss it tomorrow. Yes, this question we'll discuss because we have discussed the inverter mode operation, right? So we'll discuss this question and after that probably we'll stop. Okay. So yes, a full bridge converter supplying an RLE load as shown in figure. The firing angle of the bridge is 120 degree alpha. The supply voltage Vm of T is 200 pi into sine of 100 pi T volt. R is equal to 20 ohm. E is equal to 800 volt. The inductor L is large enough to make the output current IL a smooth DC current. So now IL, that is the output current, IL is constant here. IL means your I0. The real power fed back to the source in kilowatt is, means our task is to find the how much power is fed back to the load, to the source. Now we can check here. Here they have given alpha is greater than 90 degree. You can check the polarity of the E. It is a reverse polarity, na? So it is a inverter mode of operation. Okay, it is a inverter mode of operation. So let me write alpha is equal to 120 degree. Next, the supply voltage Vm of T, 200 into pi into sine of 100 pi T. R is equal to 20 ohm. E is equal to 800 volt. Inductor L is large. Okay. IL is constant. Our task is to find the power P. Now you can check. Okay. It is like a continuous conduction. Na? L is a large means what? Continuous conduction. Okay. So how will be the waveform of, yes, how will be the waveform of V0 here? Omega T 0 alpha is 120 degree they have given. Okay. Pi, this is 2 pi. So alpha will be somewhat here. 120 means it is alpha. This is your pi plus alpha. So the waveform, V0 waveform will be like this. After this, it will be this, right? We discussed this yesterday. So or no, right? This is a Vs only. Now you can check V0 average. No, before that, I0 average is how they have given. It is a constant, na? So I0 is your constant current. Yes. Now, what is the P0 here? That is the output power. P0 average, suppose I want to find. What is the expression? Yes, you can check I0 is constant. So P0 is nothing but integration 1 by pi. Okay, 1 by pi integration from alpha to pi plus alpha. 1 by pi integration from alpha to pi plus alpha, na? Right? It is a Vm sin omega t into I0 into d omega t. Again, I0 is constant, so we can take it outside. right? So let me write it as 1 by pi integration from alpha to pi plus alpha into, it is a V0, let me write it as into I0 into d omega t. Again, I0 is constant, so we can take it outside, into, this will be like 1 by pi integration from alpha to pi plus alpha. This is V0 means Vm into sine of omega t into d omega t. So what this term indicates? Yes, this bracket, it indicates your V0 average only, na? So if your I0 is constant, your P0 average is equal to V0 average into I0. Please keep it in mind, right? P0 average is equal to V0 average into I0, right? Now, I0 means they have given now IL actually in this case. Okay, so how to find the V0 average? We know it is a continuous conduction, na? So it is like a 2 Vm by pi into cos alpha, right? 2 Vm by pi into cos alpha. So let me write it as I0 into 2 Vm divided by pi into cos alpha. So you can check what is I0 they have given. Yes, it is a, yes, I0 actually they have not given. Okay, we'll find. Okay, so this is actually your P0 average. Next, let me write it as P0 average. So first, can we find the V0 average? V0 average means this term. Okay, and let me write here better. V0 average. Right. So here I am replacing this bracket with V0 average. So now can we find V0 average? Now V0 average is equal to same 1 by pi integration from alpha to pi plus alpha. It is a Vm into sine of omega t into d omega t. So which is equal to 2 Vm by pi into cos alpha, na? Right? 2 Vm by pi into cos of alpha. This is your V0 average. Now what is a Vm? You can check supply voltage. 200 pi, it is a peak value, na? So we can write it as 200 pi. 200 pi into these two as it is, divided by pi into cos of alpha is 120 degree they have given. So if you check pi will get cancelled. So it is 200 into 2, that is a 400 into cos 120. Cos 120 is minus 0.5. So it is a minus 200 volt. This is your V0 average. So average output voltage is negative only, right? Average output voltage is negative. So now can we find P0 average? So before that, what is I0 average? RL E load. What is I0 average? V0 average minus E divided by R, na? V0 average minus E divided by R, because average voltage across inductor is 0. So it is equal to minus 200 minus E. Okay. Just a minute. Yes. Here E is reversed. Here E is reversed. So whether can I directly use this expression or I need to modify? Please listen. This is a I0 average expression when we are having E is connected such a way that positive plate upper side, negative plate lower side. Now in this case, you can check now in this case E is reversed, na? So if this E is reversed, can I write? Suppose this is a V0. Let me write here. Suppose this is a V0 plus minus, here it is a V0. Okay. Can I write V0 is equal to VL plus VR? And this is E now. Okay. So this E will be minus E. Or you can write KVL plus V0 minus VL minus VR plus E na is equal to 0. So therefore V0 is equal to VL plus VR minus E here. Out of that, this your VL average is 0. So can I write V0 average is equal to VR average minus E. And what is VR average? I0 average into R, na? I0 average means in this case it is IL. Okay. So it is a V0 average is equal to I0 average into R minus E. So what it indicates? Your I0 average. Therefore, I0 average, I am writing here, is equal to what? V0 average plus E. This is important. V0 average plus E divided by R. V0 average plus E divided by R. Is this clear? Why it is a plus E? Because the polarity of the E is reversed. Yes or no? So here I cannot blindly use this expression. I need to write it is a plus E only, right? So it is a minus 200 plus. What is the E? They have given it is a, yes, 800 volt. Okay. So it is a 800 and divided by R. What is the R value? 20 divided by 20. So if you check, it is a 600 by 20 means 30 ampere. This is your I0 average, right? So now I0 average is 30 ampere. So now what is the P0 average? Therefore P0 average is V0 average into I0 average. Your I0 average means your constant current I0, okay, which is equal to V0 average into I0 only. So it is V0 average is minus 200, na? Minus 200 into 30. So you can check it is a minus 6 kilowatt, right? Minus 6 kilowatt. What that minus indicates? What is the meaning of power is negative? Means actually load is not consuming the power, na? Load is supplying the power. Yes or no? That's why it is a power fed back, right? So here, as P0 average is negative, the meaning is load is supplying power. Load is supplying power to source. Load is supplying power to source, right? So therefore power fed back. Power fed back is equal to your 6 kilowatt. Power feedback means what? The power which is fed by the load to the source, that is the 6 kilowatt, right? Okay, yes. Okay, so we'll stop here. Tomorrow we'll discuss some additional numericals and we'll discuss the concept of source inductance. Okay, tomorrow we'll finish the single phase rectifiers and then we'll start the three phase rectifiers. In the three phase rectifiers, we are going to discuss the diode rectifier, okay, and after that the SCR rectifier, that is a controlled and uncontrolled rectifier, okay, for R load, RL load and RLE load, right? Okay, yes.
Sir, can you please share your number?
Okay. Please note it. It is 73. Just a minute. 73 87 86 4360. 73 87 86 4360. Right?
Sir, the same.
Yes, sir.
Hello, sir.
The same problem. I have a doubt, sir. Right?
Which problem?
The last problem that you took.
Okay, here, huh?
Sir, in this from period alpha to pi, actually the inductor is charging, no, sir.
Inductor is storing the energy.
Yes, sir. During this process of storing, the current will pass through R, resistance R also, no, sir.
Yes.
So during that time, the resistor is dissipating the energy. So that part of the energy is not being sent back to the source, no, sir.
Yes.
So in that case, the power returned will be the energy that is being between pi and pi plus alpha.
No. Don't think in that way. You can check here. In this circuit, okay?
Okay, sir.
This current is how much? 30 ampere we got. Now you can you find the power supplied by this EMF?
800 into 30.
800 into 30. Please check how much is this that one?
That will be around 24 kilowatts.
24 kilowatt. Now you can find the power consumed by the resistor.
Yes, sir.
It is a 20 into 30 square, na? I0 RMS square into R.
Yes, sir.
So how much? It is 18 kilowatt.
18 kilowatts.
So 24 minus 18 means remaining is a 6 kilowatt feedback.
Okay, sir. Okay, sir.
Right?
Okay, sir.
Yes.
Hello, sir.
Yes, please.
Sir, first paper one.
Slide number
At the
one.
starting of class, maybe 2 or 3, sir.
Okay, okay. Just a minute. Okay. This one.
Hi,
Here
yes,
it
sir.
is.
Sorry, in this asymmetrical, the conduction of time of the each diode is pi by omega, no, sir. How can is the pi plus alpha? Could you explain that one?
Yes, yes, yes. Please repeat.
Conduction of time of each diode is pi plus alpha in the in the asymmetrical. How is pi plus alpha, sir? It's a pi plus omega, no, sir.
In asymmetrical, you are saying
Hi, yes, sir. Could you explain that one, sir?
this is stable.
No, no, next one, sir. Asymmetrical conduction time of the diode.
Okay, here asymmetrical
Last one.
conduction time of each diode.
Hi, yes, sir.
Okay, okay. You can check here. Diode D1 is in on state in pi to pi plus alpha.
Hi, yes, sir.
D1 is in a conduction mode pi plus alpha to 2 pi also.
Yes, sir.
Here also D1 is in a conduction mode 2 pi to 2 pi plus alpha. Whether diode D1 is there in an interval number 1? No. So you can check diode D1 is there in the circuit from pi till 2 pi plus alpha, na?
Yes, sir. I
So
forgot
that's why
last
it is
time.
2 pi plus alpha minus pi divided by 1.
Okay, sir. Yes, sir. I got
Right?
it.
Here you can
Yes, sir.
check for
Thank you.
D2 also. D2 is in a conduction mode from this interval, and this interval. So again, three
Yes, sir.
intervals. So that's why the same you will be getting, right?
Yes, sir. Sir,
Yes.
sir, day before actually I sent that question. You did not send that solution.
Which one? Which one?
16th one, there is a junction capacitor is there, no, sir.
Okay, you only. Yes. Your name is?
Imtiaz.
Yes, yes. I will give you the answer. Okay.
Okay, sir.
Yes, yes. I will WhatsApp.
Thank you, sir.
Yes.
66F, sir.
66F.
Ah.
66. No, just a minute. Okay. Yes.
Sir, here we found the angle, no, sir, cos alpha angle, cos of that.
Where?
That dBF. No,
In
cos of 60 degree, cos of 60 degree. Before page. Sir, here we found cos of 60 degree, no, sir. It is the angle between V1 and I1, sir. How we need to calculate, sir? It is 60 minus 60 degree or 60 minus 0 degree, sir.
Okay. No. Actually, it is a minus 60 degree. It should be minus 60 degree.
Okay, sir. Because cos is
lagging, current is lagging.
Okay, sir. While calculating that, we need to include omega t also, sir, or only the angle that 0 and 60.
Only the angle.
Okay, sir. And another doubt, sir, in 12F.
1,
2, 12F.
Okay, 12F. Okay. Right.
Sir, here how we need to find it is odd function, sir. By shifting, how you say it is odd function, sir?
Okay. You can check. Odd function means what? F of minus t is equal to minus f of t, na?
Yes, sir.
Now you can check. This is a positive cycle. This is a negative cycle.
Yes, sir.
After this, again there will be a positive cycle.
Yes, sir. It will be repeated.
So now you can check here. Before this, which cycle will be there?
Negative cycle, sir.
Negative. That will be from. Let me draw here. Okay. 0 till definitely it will be from 0 till minus pi, na?
Yes, sir.
Okay. Now you can check. F of minus t means what? Suppose I am finding it as a pi by 2, minus pi by 2. At minus pi by 2, what is the value of this is dash? It is
minus
I0, na? Minus I0.
Minus I0.
Right. So I am writing minus f of minus t is a minus I0. Yes or no?
Yes, sir. Yes, sir.
Okay. And that should be equal to minus f of t, na?
Yes, sir.
That should be equal to minus of it is minus pi by 2, so it should be plus pi by 2. At pi by 2, what is the value?
Plus I0.
And that minus as it is, and this I0. So whether both are matching? Yes.
Yes.
So that's
sir, and another doubt, sir, in semi-converter, symmetrical circuit.
Symmetrical circuit. Okay. Symmetrical,
Sir, here you told after theta, T1 and D1 will conduct, sir.
After theta,
After theta, why T1 and D1 is not conducting, sir? After theta itself, inductor is releasing the energy, but why T1 and D1 not conducting?
because the thing is, you can check from theta till pi, it is like a higher potential, it is a lower potential.
Okay, sir.
So due to this, actually your diode will be in a reverse bias mode.
Okay, sir.
D1 will be in a forward bias mode only after 2 pi. Sorry,
And that
after
is pi.
not 2 pi, after pi.
Okay, sir. But in that case also, still our energy stored in the inductor is very large. You have told it many times, it will be more than the source voltage. So it can thyristor will be turned on and diode also will be turned on. In many cases you told like that, no, sir.
Yes. Okay.
But
check. At theta, what is the voltage across inductor?
at theta, the voltage across inductor will be 0, I think.
0. Okay.
Ah.
Just after the theta, what is voltage across inductor?
Negative.
Negative. What is the value of that voltage? Whether the voltage will be very high or less?
Magnitude, sir.
Magnitude. After theta, voltage across inductor will be increasing, na?
Yeah, slightly increasing, sir.
Yeah, it will be increasing, na? After theta, it will be increasing in the negative values.
Yes, sir.
So at theta it is 0. So just means between theta to pi, the voltage across inductor will be plus here, minus here, VL, na?
Okay, sir.
Now you can check between theta to pi. Actually, your Vs means this potential will be greater than that of this potential.
Okay, sir.
That's why it is not conducting.
Okay, sir. That's it, sir. Yes, sir. Thank you, sir.
Okay.
No, sir.
Yes, please.
Sir, in 22F page number.
22F. Okay. Yes.
In that we shifted that IS waveform in alpha by 2, na? So why
Yes,
we this shifted and we calculated done for IS dash,
Okay.
not for IS?
No, actually the thing is, suppose if I want to find the Fourier series expression of this waveform, IS,
Yes.
then it is a bit lengthy process. Means what? We need to find A0 by 2 will be definitely 0. No problem. Average value is 0. We need to find the AN also. Because
Okay.
this function is neither even nor odd, na?
Yeah.
So we need to find the AN also. We need to
This
find
is
the
half wave
BN
symmetry
also.
function.
Yes, half wave symmetry, but it is neither odd nor even.
Okay.
So that's why
So-
AN will be non-zero for this signal, for this
So-
function. So
so
we need to
okay, for-
calculate AN as well as BN. But what I have done, in order to take the advantage of that Fourier series conclusion, na?
Okay, for easy calculation only.
Yes, for easy calculation. If you find,
Yes, sir.
if you simplify this function IS also, as it is for if you find the AN, if you find the
Sir,
BN, na?
actually, I learned this topic in previous class that Sai
Okay.
Baba sir told. That is, they are solved only without shifting. It means they all
Okay.
calculation done without shifting. So I am little bit confused why you are taking this shifting process and
No, it is
that-
only for making calculations easy.
okay. Because
Right.
in that my notes is written in without shifting, na.
Okay. Huh.
Thank you, sir.
Okay. Yes.
Hello, sir.
Yes, please.
Sir, last
Sir,
two
why,
last
sir,
two
why
seconds.
are we,
Just
why
a
are we
minute.
shifting
One
it
by
by
one.
alpha by 2 and not alpha?
Why where?
Shifting it by alpha by 2, not by alpha.
Not by alpha. Okay. If you shift by alpha, please check how will be the waveform and whether you will be getting the odd signal or not. If you shift by alpha means what? It is like this alpha will come here. Right?
Yes, sir.
This-
Yes, sir.
This pulse width is pi minus alpha, na? So from omega
Yes,
t
sir.
0 till this pi minus alpha, you will be having a I0.
Yes,
Let
sir.
me draw the signal after shifting that alpha. Okay, you will understand. This is omega t 0. Okay, let me write it as IS dash. Okay, after shifting the alpha. Okay, here. So it will be like from this instant Yes, from here to this will be your pi minus alpha, na? Right? This is pi minus alpha, na,
Yes,
pulse width.
sir.
So that's why 0 to pi minus
Yes,
alpha.
sir.
This pulse width is again pi minus alpha. Again from pi to pi plus alpha means for next alpha radian we'll be having a 0, na? So pi minus alpha to alpha means it is a pi now. Next from pi and this pi plus alpha to 2 pi, na? This pulse width is again pi minus alpha.
Yes, sir.
So into this pi, I need to add the
Yes.
pi minus alpha. So if I add this pi minus alpha, pi plus pi minus alpha means it is 2 pi minus alpha, na?
2 pi minus alpha.
Right?
Yes,
And
sir.
after that, from 2 pi minus alpha to
Yes,
2 pi,
sir.
we'll be getting it as a, this is 2 pi, na? We'll be getting it as a 0
2
again.
pi. Yes.
Now you can check.
Yes, sir.
If this is the function, okay, positive cycle 0, negative cycle and 0. So before this 0, which waveform will be there? Whatever the waveform we have, na, from pi to 2 pi, the same will appear here at this side.
Yes, sir.
So the waveform should be like, will be like this. So from this 0 till this 2 pi minus alpha means it is like minus alpha. It will be 0. After that, we will be having this type of waveform, negative, right? That will be
Yeah.
from minus alpha to this instant, means somewhat here. Now you can compare. Here it is positive, here it is 0, na?
Okay.
So whether it is
sir.
a odd signal, no.
No.
In order to get
No.
the odd signal,
Yes,
you need to shift by alpha by 2 only, right?
Okay. Yes,
Sir, how you
Okay,
are
thank you,
saying
sir.
average value is 0, sir?
Okay. Average is 0, na, because you can check area under this plus area under this.
Okay, sir.
Positive, negative, average will be 0, right?
Okay, sir, I have general doubt, sir.
Yes.
If cos of minus theta is equal to theta, sir.
Yes, cos of minus theta is theta, na?
Cos of pi minus theta, sir.
Cos of pi minus theta is equal to minus cos theta.
In one expression, you have taken plus cos theta, sir.
Plus,
Cos theta, sir.
no, check once. Do you know the slide number?
No, sir.
Okay. I think in this expression only we will be having. It is no, it is a 1. It's cos square, you know? Yes. So in this expression only will be having. Where I have taken. Okay. Please check.
Okay, sir, I will see and I will tell
Yes.
you.
Please check once. Okay. Next.
Hello, sir.
Yes,
Sir,
please.
second last problem, sir.
Second last problem. Okay.
Second part.
Just a minute. Second part, right? This one, na?
Yes, sir. Sir, what if we have to calculate input power factor using distortion factor and distortion input factor, sir? Distortion power factor.
When
How would-
overall,
Yes, sir. How would you calculate distortion factor if the second part of the data is given, sir?
means third harmonic is given.
Yes, sir.
Okay, then if the third harmonic is given, then distortion factor will be like that only. IS1 RMS divided by your IRMS.
Or the third harmonic part will be, I think, third harmonic RMS divided by I0 RMS, right, sir?
No. Actually, the distortion factor definition is only for fundamental.
Okay, sir.
Are you getting the point? If they give the data like this, means voltage also third harmonic and current also third harmonic, na? Then we need to find the whatever we discussed, na, P1 plus P3. In
Yes,
that
sir.
way only we need to find the total power.
Okay.
If
So-
any
so-
one of them, suppose if voltage is having only sinusoidal, current is having sinusoidal plus harmonic, na? That is fundamental plus harmonic.
Yes, sir.
Then we can find whatever we discussed, that is input power factor is equal to your DF plus DPF. But if voltage is also having some harmonics, current is also some harmonics, we cannot use that expression,
Okay, sir.
right?
So this is the only way we have to go.
Yes, this is the only way.
Okay, sir. Okay, thank you.
If any one of them is suppose voltage or current, if any one is pure sinusoidal, then in that case we can find the input power factor like that. Because what the thing we observed in our converters, voltage is pure sinusoidal. Now we are giving as an input pure sinusoidal.
Yes,
Right?
sir.
So that's why that method is there for converter. But this problem is actually general problem. Right?
Okay.
Sir, 46, sir.
46.
Yes, sir.
Okay. Yes. 46.
Is continuous conduction before period.
Numerical is there?
Yes, sir. Yes, sir.
Which numerical?
Sir, I will tell.
This one, I think this one only.
Yes, sir. Yes, sir. Sir, continuous conduction means only current only continuous, sir.
Yeah, current is a continuous.
Yes, sir. But the voltage need not be continuous.
Voltage need not be continuous. Right?
In any
Continuous
case.
conduction means your operation will be continuous. Devices, yes, current will be continuous actually. You can say in that way, right?
Yes, sir. Output voltage need not, sir.
Yes, if current is continuous, definitely your output voltage depends on which devices are there in a conduction mode, na?
Yes, sir.
Right? Okay.
Yes, sir.
Yes.
Hello, sir.
Sir, average output power we are taking VRMS and IRMS, sir.
Where?
Yes, sir. That's the doubt I have, sir. Under which
Okay, no, the
case?
thing is actually we are having different cases.
Yes.
Actually, the average output power means P0 average.
Yes, sir.
Which is equal to what? 1 upon your periodic angle of your V0 and I0 waveform.
Yes, sir.
Integration over that whatever the periodic angle you will be having, 0 to that periodic angle.
Yes,
Okay,
sir.
into V0 instantaneous value into I0 instantaneous value into d omega t. But suppose if your current is constant,
Yes, sir.
then your average power, because any one is constant, suppose voltage is constant, current is varying, or current is constant, voltage is varying,
Yes,
then that whatever the constant term is there, that we are taking outside,
Yes, sir.
So that's why it is that term into whatever the remaining term is there, integration part.
Yes,
That
sir.
will be like your average value of that respective voltage or current.
Yes, sir.
So if the current is constant, okay,
Yes,
then your average power will be V0 average into I0.
Yes, sir. Yes,
That is the
sir.
current magnitude.
Okay, sir.
If suppose purely resistive load is there, in that
Yes,
case,
sir.
both are varying,
Yes, sir.
So there P0 average is equal to V0 RMS into I0 RMS.
Yes, sir. Yes, sir.
Right? In that,
Yes,
in
sir.
this way, that will vary actually. Okay.
Yes, yes, sir. Thank you, sir.
Okay. Okay.
Hello,
Yes.
sir.
Yes.
Sir,
Please.
from last to second problem, sir.
Just a minute. Last 2 seconds.
Sir, in the next formula, sir, VRMS equals to.
That considering the third harmonic.
Yes, sir. Then why not considering the fifth harmonic, sir?
Okay, okay, I will tell you.
Correct.
In this, right?
Yes, sir. No, sir. Write some formula, sir.
Here,
Yes, sir. Yes, sir.
Here it is. Here it is.
To V1 square RMS plus third harmonic. Yes, sir. Yes, sir. In this.
What is your doubt?
Sir, in that VRMS, why not considering the fifth harmonic? Sir?
For voltage?
Yes, sir. For voltage.
Because for voltage, the fifth harmonic is not given. You can check this question. If voltage has third harmonic component also.
Sir?
Right? Voltage is not having the fifth harmonic. They have not mentioned,
Okay, sir. Okay.
Right? So that's why I have taken only that thing, right?
Sir, one
If
more doubt.
they told they give the statement like the voltage is also having the fifth harmonic, then we need to consider V5 RMS also. Right?
Okay, sir. Sir, one more doubt, sir.
Yes.
Sir, before this problem, sir.
Before this problem. I think this problem we discussed, right?
Sir, no.
Yeah, this one. Active.
No, sir, in this before, sir. Waveform, sir. V output equals to alpha to pi. We calculate that alpha, sir. That's problem, sir.
Yes. I think...
Waveform, sir. V output was alpha to pi.
which problem, please?
Sir, V naught average equals to maximum voltage we calculate, sir.
Yes, this one now only alpha 120.
In this problem, you wrote a voltage, sir. V output versus alpha to pi. Alpha equals to 0, sir, for maximum V naught average.
So you want me to draw the V0 this one?
Yes, sir. Yes, sir. In this one. Sir.
In
Once
this
explain
what?
it.
Okay. Actually, the thing is, we are having a semi converter now.
Yes, sir.
Okay, and in the semi converter, they have given the maximum possible average output voltage.
Yes, sir.
25% of that maximum possible is nothing but your output voltage actually. Okay.
Yes, sir.
So V0, this waveform we are having. Did you get this waveform or not?
No, sir. Can you once explain that?
Okay. In the semi converter, what we are having? We are having a 2 thyristors, 2 diodes now.
Yes, sir.
And it is given that purely resistive load.
Okay, sir.
So as the load is purely resistive, so there is no point like inductor storing energy or releasing energy.
Releasing energy. Okay, sir.
Right? So that's why at alpha, suppose if I apply the gate signal to thyristor T1 now,
Yes,
so current will flow from Vs, T1, load, D2 and again back to the Vs.
Okay, sir.
V0 will be equal to Vs.
Yes, sir.
This will continue till pi only.
Okay, sir.
So we'll be getting alpha to pi, this type of waveform, right?
Okay, sir.
Pi to pi plus alpha, it is like circuit will be at the rest position now, because we are not applied the gate signal to second thyristor.
Okay, sir.
At pi plus alpha, we are going to apply the gate pulse to thyristor T2, so that T2 and D1 will be in a conduction mode.
Okay, sir.
So current will be flowing from Vs, T2, load, D1 and again back to the Vs. So again V0 will be equal to Vs.
Yes, sir.
So we'll be having this type of waveform. Now they get, if you want the maximum average output voltage, na,
Yes, sir.
the meaning is this alpha should be minimum.
Minimum.
Why? Because you can check your V0 average is proportional to 1 plus cos alpha, na?
Yes, sir.
If alpha is minimum, definitely your V0 average will be maximum, na?
Okay,
You
sir.
can check alpha is 90 degree. You can check alpha 120 degree. Put alpha is equal to 60 degree. Alpha is equal to 30 degree. You will get, because cos alpha, cos 0. If alpha is 0 degree means cos 0 is 1.
Yes, sir.
And whether the cos alpha value will be greater than 1 possible? No.
No, sir.
So maximum possible value of cos alpha is 1 only, na?
Yes, sir.
And that will be possible at alpha equal to 0 degree.
0 degree.
So that's why at alpha we have written the maximum value is alpha equal to 0 degree, right?
Okay, sir. That case only we not average maximum. Okay, okay.
Yes, that's why we have calculated maximum V0 average. If alpha is 0 degree means what? In this waveform you can check if alpha is 0 degree, the waveform will be like this, na? It will be from 0, it will start like this. So what is the area under this curve? It will be maximum, na?
Yes, sir.
Right? So like this. Similarly, if alpha is 0 means to thyristor T2, we are supposed to apply the gate pulse at pi, na?
Yes, sir.
So that's why we'll be getting this type of waveform. It is like your diode rectifier.
Okay, sir.
Right? So
Thank you, sir.
okay. Yes. Yes, next.
Sir, 54, sir.
54. Okay. 54. No, it is a blank.
I not
53.
average.
Yes.
No, sir. Derivation, sir.
I not average derivation. Okay. This one. Here it is.
Yes, after slide, sir. 52.
Okay, this slide.
Sir, here expression, sir, minus cos of pi minus theta plus cos theta means it minus cos theta plus cos theta, no, sir.
No. Cos of pi minus theta is minus cos theta. This minus and this minus cos will be plus, na?
Okay. If cos of minus theta means it's cos theta, sir.
Cos of minus theta is, you can simply put in calculator. You can check cos 30 degree. It is a 0.866. And check for cos of minus 30. It will be 0.866. Means cos minus theta is cos theta.
Okay.
Cos of pi minus theta is minus cos theta.
Okay, sir. Thank you, sir.
right? Okay, okay, yes.
Hello, sir.
Please.
Sir, in one question with RE load, sir.
RE load,
Sir.
numerical,
Yes, sir.
RE. This is only or different?
This, sir. Sir, in this I had a small doubt.
Okay.
This 200 volt, we are directly taking it as E and not as the terminal voltage, sir.
What about 200 volt we have taken?
As E, na, sir. We don't have to take it as terminal voltage across the battery.
Yes, we have taken it as a terminal voltage E only.
No, sir. While seeing the figure, I got a small confusion. That is, this
No. It is. You can
It
read.
seems
Read
like
the very
different.
first statement. You can read this statement. Single phase bridge converter is used to charge a battery of 200 volt and having an internal resistance of 2 ohm. Battery of 200 volt means what? The battery EMF is 200 volt.
Okay, sir.
It is not like that voltage across voltage between these 2 points is 200. No.
Okay.
Right? They have
Yes.
indicated this is as a shaded or dude. Why? Because this is a battery actually, internal resistance and a EMF, right?
Sir. And that EMF is taken.
Yes, EMF we have taken it as a 200.
Sir. Sir, and one more doubt, sir, in order to find the input power factor,
Okay.
because voltage is sinusoidal and current is actually non-sinusoidal, they are using that distortion factor into the displacement power factor.
Correct.
So what if the voltage was also not non-sinusoidal? Then what we would do, sir?
Then how to find that we discussed now? If the voltage is also having the third harmonic component, then I need to find that power factor is equal to real power divided by your apparent power.
Okay, like that we'll find.
Like that only we need to find, right?
Okay.
Okay.
Thank you, sir.
Okay.
Sir, hello, sir.
Yes, please.
Sir, 21F, sir.
21.
1F.
21F. Yes.
Sir, you have now explained why we have to take only alpha by 2, sir, and why not alpha means you drawn one curve, no, sir.
Yes.
Sir, once
that I erased.
Yes, sir. I actually when you will take alpha, will not get f of minus t is equal to minus of f of t, no, sir.
Yes.
Sir, that once you draw that curve, sir, please.
After by shifting alpha, na?
Oh, yes, sir, by shifting alpha. Sir.
Okay, just a minute.
Okay, sir.
Yes. So omega t. This is let me write is dash. Okay. After shifting alpha means this point will be at 0.
Yes, sir.
So this pulse width is like alpha to pi means pi minus alpha, na?
Yes, sir.
So from 0 till pi minus alpha will be having this pulse, that is I0.
Yes, sir.
Right? So this will be till pi minus alpha. Okay.
Yes, sir.
Now you can check waveform from pi to pi plus alpha means alpha radian we're having 0.
Yes, sir.
So again from this instant I need to add alpha radian 0 now. So pi minus alpha plus alpha means pi here. Right?
Yes, sir. Yes, sir.
Next from pi plus alpha. Now I have shifted by alpha means this pi plus alpha will become pi, na?
Yes,
that's
sir.
what is pi. So from pi plus alpha to 2 pi, it is a minus I0. You can check
Yes,
this
sir.
pulse width 2
Yes,
pi
sir.
minus in bracket pi plus alpha. So it is a pi minus alpha only. So from here till pi
2
plus
minus
pi minus
alpha.
alpha means pi plus pi minus alpha means 2 pi minus alpha, na?
Yes, sir.
Right? So it will be 2 pi. And after that again till 2 pi we need to maintain the 0, na?
Yes, sir.
Let me write here. Okay. Yes. So it is omega t until 2 pi. Yes, it will be like this. This is 2 pi. Okay.
Yes, sir.
So now if this is the waveform we're having, right? 0 to pi this shape and pi to 2 pi this type of shape.
Yes, sir.
Again, after 2 pi, what will happen? After 2 pi, again, this will repeat, na? This,
Yes,
whatever
sir.
the pulse is there, this will repeat. So before 0, which pulse will be there?
Pi to 2 pi, sir.
Pi to 2 pi pulse. So you can check pi to 2 pi means what? This is a 0 na here.
Yes, sir.
And till minus pi, I need to check here. Pi to 2 pi means what? This 0 means this 2 pi now.
Yes, sir.
Right? So from 2 pi to 2 pi minus alpha means 0 to minus alpha here. It will be 0.
Yes, sir.
After that, from here to here, we are having the pi minus alpha pulse, na?
Yes, sir.
So this pulse will be like this, right? And after that, again same. So this will be your minus I0. This is your after shifting by alpha radian.
Yes, sir.
Now you can check whether it is a odd signal or even signal. It is neither, na?
Yes, sir.
Right?
Yes, sir.
That's
Okay,
why
sir.
we cannot shift by alpha, right?
Okay, sir. Thank you, sir.
Yes. Okay. Yes. Next.
Good evening, sir.
Good evening.
सर क्या आप सेमी कन्वर्टर विथ आल लोड फिर से एक मतलब एक्सप्लेन कर सकते हैं जब आप
कौन सा
सेमी कन्वर्टर विथ आल लोड
R load ना that numerical
नहीं न्यूमेरिकल नहीं सर आप सर्किट डायग्राम एक्सप्लेन करें
circuit diagram and the waveform ना
हाँ सर
okay just a minute let me erase this which semi-converter you want, symmetrical or asymmetrical?
सिमेट्रिकल सर
Okay, symmetrical. Just a minute.
और आरएल लोड से क्यों लोड आरएल क्यों लेना आप विदाउट आर भी ले सकते ना
नहीं आर भी ले सकते सिर्फ आरएल के लिए डिफरेंस है ना उसमें दैट्स व्हाई हमने सिर्फ वो डिस्कस किया है आई विल लेट यू नो जस्ट अ मिनट सपोज हियर सिमेट्रिकल ना
यस
थायरिस्टर T1 डायोड D1 थायरिस्टर T2 डायोड D2 right you want the R load right T1 D2 T2 D1 na? This is a symmetrical. Now in this circuit what will happen at alpha we are going to trigger T1 okay am I audible
yes sir
okay so you are having Vs this type of waveform na
yes sir
0 to pi and pi to 2 pi okay so V0 will be like this at omega t is equal to alpha we are going to trigger the omega t alpha and here it is pi plus alpha okay so at alpha T1 is turned on supply voltage is positive na so T1 is turned on by applying the gate pulse so current will flow from Vs T1 load D2 and again back to the Vs right
yes sir.
so what is the V0 is equal to Vs na
yes sir.
so in the output will be getting this type of waveform this will continue till pi only because at pi what will happen supply voltage is 0 na so your load current is 0 thyristor current is also 0 so thyristor T1 will turn off at this instant from pi to pi plus alpha what will happen none of the thyristor will be now on state current will be 0 na
yes sir.
right and at pi plus alpha we are going to apply the gate pulse to thyristor T2 now so when gate pulse is applied to T2 and at this instant you can check supply voltage is negative na so it is minus here plus here current will flow from Vs T2 load D1 and again back to the Vs in this loop current will flow if the current is flowing into this loop what is the output voltage it is again Vs na
yes
so that's why this type of waveform will be getting
I
I
know
can use semi converter for R load also RL E load also right but we explained only for RL load because the freewheeling action is present there na
yes sir.
inbuilt freewheeling action is there right freewheeling diode is need not to be connected right
सर आई नॉट कांस्टेंट नहीं रहता ना सर इसमें
purely resistive में I not constant नहीं रहेगा RL में रहेगा.
अब RL RL कुछ भी यूज कर दो, कुछ भी प्रॉब्लम नहीं.
यस यस, RL और RLE अगर हम यूज करते हैं और लोड अगर इंडक्टर अगर हाईली इंडक्टिव है ना, लोड अगर हाईली इंडक्टिव है, देन एंड ओनली देन आवर लोड करंट कांस्टेंट होगा.
अब कांस्टेंट करंट रहे तो प्रॉब्लम होती ना सर, हाई करंट की वजह से. उससे
नहीं नहीं, प्रॉब्लम क्या है? कांस्टेंट करंट मीन्स अच्छी बात है एक्चुअली, बिकॉज व्हाट वी एक्सपेक्ट कि दिस इज अ रेक्टिफायर ना. व्हाट वी एक्सपेक्ट कि रेक्टिफायर शुड गिव द कांस्टेंट डीसी आउटपुट.
यस सर.
अगर मुझे लोड में करंट कांस्टेंट मिल रहा है मतलब अच्छी बात है ना ये.
यस सर.
दिस इज एक्चुअली आइडियल केस. एक्सपेक्टेड कि आपका लोड वोल्टेज और लोड करंट कांस्टेंट होना चाहिए, बट ड्यू टू द स्विचिंग क्या हो रहा है कि हमें कांस्टेंट नहीं मिल रहा है. द मीनिंग इज हमारे आउटपुट में कुछ तो हार्मोनिक्स प्रेजेंट है, राइट?
यस सर. थैंक यू.
ओके,
Good evening, sir.
हाँ, गुड इवनिंग.
Sir, I have one doubt in full bridge converter, sir.
Where?
Actually, yesterday's class, sir. Full bridge converter.
Okay, yesterday's class. In that,
Sir. Sir, even though we short circuit the below thyristor, it will work. It will work and gives the output, sir.
will you please speak a bit louder?
Sir, for example, consider this circuit, sir, in this slide.
Okay.
If we short circuit the D1 and the D2.
T1 and D2.
Sorry, sir. D1 and D2. Diode 1 and diode 2.
Here diode 1, diode 2.
Sir, if we short this diode, short circuit these diodes, converter will works and gives the output, sir.
Current will?
Converter will works and gives the output, sir.
Means you are saying that here D1 and D2 are short circuited.
Sir, even.
But how these two will be getting short circuited?
Sir, actually my doubt is if we in full bridge circuit 4 thyristors we are using now, sir.
Yes.
T1, T2, T3, T4.
Okay.
For one closed path we need 2 thyristors, sir. At least even one thyristor it will also works now, sir. Why we are using 2 thyristors in single loop?
Okay, okay. Why we are using 2 thyristors in a single loop?
Yes, sir.
Okay. Means so here we are using 2 thyristors only, na, one thyristor in one loop.
Yes, sir.
Okay.
Another thyristor for reverse bias loop.
Okay. So now please let me know whatever previously you were saying, D1, D2 short circuit.
Yes, sir. Like that.
Suppose D1, D2 short circuit, na? Yes or no?
Yes, sir.
So what will happen here? You can check. Suppose supply is positive. If these two are short circuited, na, this will potential will appear. This potential will appear here, na?
Yes, sir.
Right?
Yes, sir.
This potential will appear here. This is short circuit, means this will appear here. So it is like directly across source you will be getting a short circuit.
Okay.
Are you
Okay.
getting?
Source will be short circuiting.
Your source will be getting directly short circuited, na?
Yes, sir.
Right? So your source will get damaged.
Yes, sir.
Right?
That's
Okay.
why we are putting either diode or thyristor, sir.
Yes, yes, yes. We need to put that devices, those devices, right?
Okay, sir. Okay. Thank you, sir.
Okay, okay, yes.
Sir, in single phase semi-converter symmetrical configuration, sir.
Yes, this is only, huh?
With RL load, sir.
RL load you want, okay.
Slide number 2, I think, sir.
Just a minute.
Okay, sir.
Yes.
In that symmetrical configuration from pi to pi plus alpha, why T1 and D1 are conducting, sir, not T2 and D2?
Pi to pi plus alpha, na?
Yes, sir.
Okay, why T1 and D1 are conducting? Why not T1 and D2?
No, sir, T2 and D2.
At pi, whether we have given the gate pulse to T2?
No, sir.
Then how the T2 will conduct? We are giving the gate pulse to T2 at pi plus alpha, na?
Yes, sir.
So at pi plus alpha, your T2 will start conducting. So pi to pi plus alpha, how the T2 will conduct? T2 will not conduct because we have not applied the gate signal, right?
Sir, once indicate the direction of current flow, sir.
Which,
During the
which
demo.
current? Which current?
From source to load and load to diode D1 and T1.
T1 and D1.
Yes, sir. Once indicate the direction of current flow.
No, but when T1 and D1 are in the conduction mode, na, at that time current will be flowing like whatever the inductor energy is there, na, that energy will be circulating through this loop only.
Okay, sir.
This current will not go into this your supply side.
Okay, sir.
Because here it is opposition, na.
Here it is opposing, sir.
Actually, the pi to pi plus alpha, your Vs will be like this minus plus, na.
Yes, sir. Negative.
So the thing is, inductor can either release energy through T1 D2 or T1 D1.
Yes, sir.
But if inductor releases energy through D2, na,
Yes,
then
sir.
it is like when inductor releases energy like this through D2, Vs, T1, and again back to the load, na. In
Yes.
this case, it is like inductor energy will be opposed by the supply energy because supply plus here minus here. Supply will try to circulate current in this direction, na.
Yes, sir.
And inductor is trying to circulate the current in this direction, that is D2 and after Vs. So
Okay.
both will be opposite, na. So
Okay.
that's why, and again you can check alternate path is also available, that is through T1 D1. So generally current flows, current takes the path with a lesser opposition, na.
Okay, sir. Got it, sir.
Right. So that's
Another doubt, sir.
yes, please.
In single phase fully controlled rectifier with RL or RL erode, in that we have calculated a distortion factor, na, sir.
Yes, that input power factor and distortion factor, right?
Yes.
Just a minute. Okay, in which case you want quasi square wave source current or square wave?
Square wave, sir.
Square wave, okay. Yes, this is na,
Distortion factor.
distortion factor you want, okay. Yes,
In that, how IS RMS equal to I naught, sir? I didn't get that.
IS RMS is equal to I naught, okay. You can check this IS waveform. This is our IS waveform, na?
Yes, sir.
So from 0 to 2 pi, whatever the waveform we are having, same will repeat from 2 pi to 4 pi.
Yes, sir.
Now, if I want to find the RMS value of this, right?
Yes.
RMS means what? Square root of mean of squared value, na?
Yes, sir.
So first we need to find the mean of the squared value and then we need to put it into the square root.
Yes, sir.
So mean of the squared value means first thing is I need to square this.
Yes, sir.
Yes or no? So what is the square of this? IS square. Negative square will be positive.
Mm.
That is I0 square, na? This is minus I0. So its square will be my I0 square.
Yes, sir.
Its square will be, this square will be I0 square again. Positive I0 square is I0 square only.
Yes, sir.
Minus I0 square is again I0 square.
Yes, sir.
So if I want to draw the IS square waveform, I am saying IS square waveform. How it will be? That waveform will be constant I0 square, na?
Yes, sir.
So if IS square waveform is constant I0 square, then what is the average value of that waveform? It is I0 square only.
Sir, aren't you considering any interval like 1 by 2 pi?
You can simplify by using the interval or simply by observing the waveform also we can find. So I am telling you by observing the waveform actually. If you want to find interval by interval, then simply you can do 1 by pi integration from alpha to pi plus alpha I0 square into d omega t.
Okay, sir.
Right? In this way you will get the answer, right?
Okay, sir. Thank you.
Okay. Right? Okay. Yes, Bijay Sahu, are you there? You have posted one message. Bijay Sahu. Okay, nothing yet. Right. Yes.
Sir, in asymmetrical single phase semiconductor, from pi to pi plus alpha, is this the same logic as pi to pi plus alpha in symmetrical semiconductor? The path followed.
Yes. Miss inductor na religious.
Yes, sir. In RL load.
Same only.
Same as in case of T1, and if we follow T1 and D2, it opposes the supply voltage. Is this the same logic as it?
Where in which you are saying?
In symmetrical configuration, sir. You told that during pi to pi plus alpha, if the inductor is discharging from source to T1 and again from RL to D2 and again to the source,
Yes.
it opposes the supply voltage.
Inductor energy will be opposed by
Opposing
the supply voltage.
supply voltage. So that in order to overcome that, we are following a path of T1 and D1, which is
yes.
So is this the same logic as is in asymmetrical also? Why we are following D1 and D2 path from pi to pi plus alpha?
Same thing is there. Okay.
Okay, that
In
means
asymmetrical, na? In
Yes, sir,
asymmetrical through D1, D2, na?
Yes, sir. It discharges L discharges through D1 and D2.
D1, D2, right, correct.
Okay, sir. Okay. Thank you, sir.
Okay. Yes, next.
हेलो गुड इवनिंग सर.
हाँ सलमान खान जी बोलिए.
जी सर, ये सिंगल फेज हाफ कंट्रोल रेक्टिफायर सर, आरएल लोड.
सिंगल फेज सेमी कन्वर्टर.
Yeah, semi converter.
Okay, हाँ.
RL load. Sir, in this you said that
Will
when
you please speak a bit louder?
Yeah. Sir, in this one, when we reverse the voltage, means after pi.
Okay.
Then the reverse path, you said that inductor will discharge through D1, T1, right, sir?
T1, D1, correct.
T1, D1. It is not discharging through D2, T1 because the source is opposing, na, sir?
Yes.
But I can see the same opposition at T1 anode, sir. Means
Same
T1
opposition
anode,
at?
T1 anode. There is
Okay.
negative at anode side and positive at cathode side. This means same opposition we are getting, na, sir?
Okay. No, but the thing is, you can check the voltage. Yes, you are saying at negative, na? Minus plus, na?
Minus plus, yeah.
But the thing is, you can check during pi to pi plus alpha, what is the supply voltage value? Comparatively less.
Yeah, supply voltage is less.
Right? Yes, so therefore our inductor will successfully overcome. Okay, due to our inductor voltage, our thyristor will be successfully in the conduction mode, that is in the forward bias mode only.
Right.
And the important thing is, if you are thinking like that, here current is flowing through the supply, na, means through the T1, it will be like this.
Right.
No, that current will not flow, because if you check, when T1, D2 will be, T1, D1 will be in a conduction mode, na? Right? If the supply is requires to complete the path, na?
Yes.
Then definitely this your T2 should be in a conduction mode.
Right, T2 should be.
And whether our thyristor will allow the reverse current? No. So that's why this path will be like your lesser opposition path.
Right, sir.
Right?
Okay. Yeah, sir, other doubt is then in this same, means D2 and D1 provide the same opposition, na, sir?
Where?
D2 and D1. We get the same opposition there, na, sir?
D2 and T1.
D1 only, diode D1.
T2 and D1.
Diode D1 and diode D2.
Diode D1 and diode D2, yes.
Overall, if you see, sir, there is same opposition, na, sir?
means when if D1 is a conduction mode and D2 is in a conduction mode.
Yeah, that's what I'm saying, sir.
Okay. Now the thing is, diode will not actually oppose for the conduction. These diodes are ideal diodes, na?
Right, sir.
They will not cause any conduction drop or the voltage drop.
Right, sir.
But the thing is, if inductor releases energy through D2 and Vs, na, you can check. Suppose inductor current is flowing like this: L, D2, Vs, T1, and again back to the D2. Okay, or back to the L. Okay.
Yes, sir.
So what is the current of the inductor that is flowing through this path? It is a upward direction, na, for Vs.
Yes, upward direction.
And Vs polarity, like there it is plus, here it is minus. Lower is plus, upper is minus. Means Vs will try to circulate current in this that is lower downward direction.
Right, sir.
So can I say that supply voltage current and your inductor current both will be opposite?
Yes, sir. We can.
So the thing is, inductor energy will be opposed by the supply energy.
Right.
So that's why actually the inductor is inductor, we can say in electrical we're having the one theory that current always follows the path with lesser opposition.
Yes, sir.
Right. So that's why the resultant current will flow. Resultant current will flow into this in this loop only. Right.
Right, sir. Okay, sir. Thank you.
Okay. Yes.
Hello, sir.
Yes, Navdeep, please.
Sir, first numerical, sir. Today, which we have done. Semiconductor converter, we are RLE load.
This one?
Yes, sir. I am not getting its output voltage waveform, sir. How you are getting?
Okay. Output voltage waveform. Here.
Yes, sir.
Okay. This is a single phase semi converter, right? With the RLE load. Okay. Yes. RLE load, and it is given that continuous conduction, na?
Yes, sir.
This is a continuous conduction. Actually, the thing is, what is happening? Suppose in this case, actually, I will let you know. Yes, here it is. Yes, suppose here instead of RL, we are having a RLE load.
Yes, sir.
Okay, now continuous conduction, the meaning is our value of inductor is high.
Yes, sir.
So at omega t is equal to alpha, what we are doing? We are applying the gate pulse to thyristor T1.
Yes, sir.
So current will flow from, yes, it is like a plus here, minus here, na? So it is plus here, minus here. Current will flow from Vs T1 load D2 and again back to the Vs. In this loop, current will flow.
Yes, sir. Yes.
That current will flow from alpha till pi only. After
Sir,
pi, what will happen? After pi, what will happen? Our inductor will release energy through T1 D2, na?
Yes, sir.
It is same as that of RL load. RLE load with highly inductive load means it is same as that of your RL load only.
Sir, I am saying before alpha. I am saying that before alpha, alpha output voltage will be E, na, sir.
Before alpha, no, that will be only for very first cycle. If you check for continuous cycle, what is happening here? From omega t is equal to alpha to pi, T1 D2 are in a conduction mode, V0 is equal to Vs.
Yes, sir.
Pi to pi plus alpha, inductor is releasing the energy. What is a V0? V0 is 0.
0.
Pi plus alpha, we are triggering the thyristor T2.
Yes, sir.
So with T2, D1 will conduct.
Yes, sir. Yes, sir.
What is the V0 from pi plus alpha to 2 pi? What is V0? V0 is same as that of the supply voltage, that is a positive.
Yes, sir. Yes, sir.
2 pi to 2 pi plus alpha, what will happen? 2 pi to 2 pi plus alpha. This inductor will again release the energy through T2 D2, na?
Yes, sir.
So now from 2 pi to 2 pi plus alpha, if inductor is releasing the energy, then from 0 to alpha also, for continuous cycle I am saying, for continuous cycle, for 0 to alpha, inductor is supposed to release the energy only, na?
Yes, sir. I was having only this doubt, sir.
Yes, sir. That's why it is a 0. That's why it is 0, right?
Okay, sir. Okay.
Right. Okay.
Thank you, sir.
Okay. Okay. Right. Yes, Mrunal, do you want to ask something? Mrunal Kesarkar.
Yes, sir. Hello, sir.
Yes, please. Yes, you are audible. Please go ahead.
Hello, sir.
Yes, please.
Sir, one small doubt.
Yes.
If order of harmonic in Fourier series is high or increases, then what is its effect on peak value and RMS value? Is it low?
No, actually the thing is, if order is increasing, na,
Okay, sir.
the peak value is decreasing.
Okay, sir.
And as the peak value is decreasing, RMS value is also decreasing. You can check we have written here. Just a minute. Yes, here you can see. Yes, yes, IS expression na here.
Okay, sir.
So you can check for n is equal to 1, it is 4I0 by pi into this term angle. Okay, into this as it is. So peak value will be like here, this term here 4I0 by pi into cos of alpha by 2.
Okay, sir.
If your n increases, so it is like divided by 3 will be there.
Yes. Okay,
n is
sir.
equal to 5, it is a divided by 5. So as n increases, this value decreases na.
Yes, right, sir.
The meaning is peak value decreases. If peak is decreasing, sinusoidal function RMS will be decreasing.
Okay, means for 3
frequency
and
is
5
increasing,
it will decrease.
right?
Okay.
Okay.
Okay, sir.
Yes.
And sir, one more doubt.
Yes, please.
Sir, 4F.
Yes.
4F.
4F. Okay. Yes.
Sir, wave.
Waveform, na?
Waveform.
This one?
Yes, sir.
Huh.
Sir, this waveform is of with diode or without diode at load, freewheeling diode at load.
No, this waveform is for single phase semi converter.
Okay.
And this is same for REL with freewheeling diode.
Okay.
Because in REL with freewheeling diode, what is happening? From pi to pi plus alpha, inductor releases the energy na, through freewheeling diode. At that time, your other 4 switches will be in off state, so current will not flow from source.
Yes, sir. Yes,
Source
sir.
current will be 0, right?
Okay, sir.
Right. Okay.
Okay. Thank you, sir.
Okay. Right. Shravan Kumar, do you want to ask?
Sir, we are doing Fourier analysis, sir.
Huh.
Only for primary side, sir. I mean source side only.
No. The thing is, actually at the primary side is AC.
Yes, sir.
And if the load is REL load or RELE load, that is a highly inductive load. In that case, whether I am getting supply, your supply voltage is sinusoidal, it is okay. But whether our supply current is sinusoidal?
No, sir.
No. So how to find the input power factor? We cannot directly find, na, because if supply voltage is sinusoidal and your supply current is non-sinusoidal, we cannot directly use that expression input power factor for finding the input power factor. Input power is equal to output power. That we cannot use.
Oh, yes, sir.
So we need to use this method. So that's why we're taking the help of the Fourier series. And what the Fourier series expression or the Fourier series tool is about, the Fourier series, it is giving the information about which harmonics are present.
Yes, sir.
So from that, we are extracting the fundamental component.
Okay.
And after that, we are finding the input power factor, right?
Sir, if the circuit contains only resistive load, then we can use input power.
Yes. For only resistive load, no need to go for this expression. Huh?
Yes.
That's why I have specifically mentioned for REL and RELE load only.
Yes, sir. Right, sir.
Right?
Yes, sir.
Okay.
And only RE load only, we did not go for this.
Yes. For RE load also, we need not to go for this one.
Okay, sir.
This is specifically for when L is present, then only.
Okay, sir.
For RE load, we know na, it is input power is equal to output power. And for RE load, what is output power? It is I0 RMS square into R plus E into I0 average divided by your source volt ampere, right?
Yes, sir. Sir, and I'm asking one favor for me, sir. If possible, after completing this entire rectifiers topic, please compare the all output voltages in terms of average and RMS for a single phase, full wave, and also.
Okay, that tabular form.
Yes, sir. Please provide, sir.
I will summarize all. Okay.
Yes,
in
sir.
tabular form, it is very difficult to put in a one slide, right?
Okay.
I will summarize one by one. Okay.
For doing problematic numericals easily, sir.
Yes. Definitely.
Thank you very much, sir.
Okay. Yes. Right. So, thank you. Thanks to all of you. Tomorrow we'll be meeting at 7. Okay.
Good night, sir.
Thank you. Good night.